What is time? The question seems almost absurd in its simplicity, yet it has puzzled humanity's greatest minds for millennia. You experience time every moment of your existence. You wake up, hours pass, you age, seasons change, and eventually you will die. Time appears to flow like a river, carrying you from past to future in an unstoppable current. But what exactly is this mysterious dimension that governs every aspect of reality? To begin our journey toward understanding whether we can escape time altogether, we must first grapple with what time actually means. The answer, as we will discover, is far more complex and strange than our everyday experience suggests. Consider the moment you are reading these words. Your brain processes the information. Your heart beats. Blood flows through your veins. Electrons dance through the circuits of your reading device. All of these processes happen in sequence, one moment following another. This is time as change. Every physical process, from the decay of a radioactive atom to the birth of a star, marks the passage of time through transformation. Without change, would time have any meaning at all? The ancient Greek philosopher Aristotle captured this intuition when he defined time as the measure of change with respect to before and after. In his view, time was inseparable from motion and transformation. A universe frozen in perfect stillness would be a universe without time. This perspective aligns with our everyday experience. We measure time by watching clocks tick, observing the sun cross the sky, counting our heartbeats. Time, from this viewpoint, is the rhythm of the cosmos itself. But there is another way to think about time, one that emerged from the revolutionary physics of the 20th century. Instead of time being merely the measure of change, modern physics treats time as a fundamental dimension of reality, as real and concrete as the three dimensions of space. Just as you can move forward and backward, left and right, up and down through space, events can be separated in time. This four-dimensional fabric called space-time forms the stage upon which all cosmic drama unfolds. In this picture, time is not something that flows or passes. Rather, all moments, past, present, and future, exist equally in what physicists call the block universe. Your birth, your current moment of reading, and your eventual death are all equally real, like different locations along a highway. The sensation of moving through time, of experiencing a flowing present moment, becomes an illusion of consciousness, not a fundamental feature of reality itself. This leads us to yet another conception of time, one rooted in the second law of thermodynamics. Time, in this view, is defined by entropy's arrow. Entropy measures disorder, and in our universe, disorder almost always increases. A broken egg never spontaneously reassembles itself. Hot coffee always cools down, never heats up on its own. This universal tendency toward increasing disorder gives time its direction, its arrow pointing from past to future. The entropy definition reveals why we remember the past, but not the future, why causes precede effects, why we age rather than grow younger. The arrow of time is carved into the very fabric of reality by the statistical behavior of countless particles, all moving from states of low entropy to high entropy, from order to chaos. Yet even this seemingly clear picture becomes murky when we examine it closely. The fundamental equations of physics, from Newton's laws to quantum mechanics, are largely time reversible. If you filmed a single particle bouncing around and played the movie backward, the reverse motion would obey the same physical laws. The arrow of time emerges only when we consider vast collections of particles, where statistical effects dominate individual behaviors. Human perception adds another layer of complexity to our understanding of time. Your subjective experience of time can stretch and compress like a rubber band. Minutes feel like hours when you are bored. Hours flash by like seconds when you are absorbed in an engaging activity. children experience summers that seem endless, while adults watch years blur together in rapid succession. Time, as experienced by consciousness, is elastic, malleable, deeply personal. Neuroscience has revealed that your brain constructs your sense of time from multiple neural processes. Different brain regions track different aspects of temporal experience. Your cerebellum helps time precise motor movements. Your hippocampus creates episodic memories that give you a sense of personal history. Your prefrontal cortex allows you to imagine future scenarios and plan ahead. Time, as you experience it, is not a single phenomenon, but a symphony of neural processes, creating the illusion of unified temporal flow. Dreams offer a particularly striking example of subjective time's flexibility. In a dream, you might experience what feels like hours or days of activity, complete with complex narratives and detailed conversations. Yet the dream occurs during just minutes of REM sleep. The dreaming brain creates rich temporal experiences without any correspondence to external, physical time. This suggests that consciousness has the remarkable ability to generate time-like experiences independently of the actual flow of physical processes. Ancient philosophers were deeply aware of these puzzles surrounding time's nature. Plato distinguished between time, which he called the moving image of eternity, and eternity itself, which was timeless and perfect. In Plato's philosophy, the physical world we experience is merely a shadow of true reality, which exists in a realm beyond time and change. The objects and patterns we perceive are imperfect copies of eternal, unchanging forms that exist outside the temporal world. This Platonic vision suggested that escape from time might be possible through philosophical contemplation and mathematical understanding. By grasping eternal truths, mathematics and geometry, the human mind could touch something beyond the temporal world. A mathematical theorem, once proven, is true forever and everywhere. The relationship between the sides of a right triangle described by the Pythagorean theorem transcends any particular moment in time or location in space. Augustine of Hippo, writing in the 4th century, offered another profound meditation on time's nature. He observed that the past no longer exists, the future does not yet exist, and the present is an infinitesimal boundary between them. Where then is time? Augustine concluded that time exists primarily in the mind, in memory of the past and anticipation of the future. This psychological view of time would influence centuries of philosophical thought and finds echoes in modern theories of consciousness and temporal perception. Eastern philosophical traditions have also grappled extensively with time's nature and the possibility of transcending it. Hindu and Buddhist concepts of cyclical time, where cosmic ages repeat in endless cycles, offer a different perspective from the linear time of Western thought. These traditions often emphasize meditation practices designed to achieve states of timeless awareness, moments of pure consciousness that seem to exist outside the normal flow of temporal experience. The meditation tradition speaks of achieving states where the sense of duration disappears entirely. Advanced practitioners describe experiences where hours pass in what feels like moments, or conversely, where brief periods of meditation contain what seems like vast expanses of inner experience. These altered states of consciousness suggest that our normal relationship with time is not fixed or inevitable, but rather one possible mode of awareness among many. But what are we to make of these different conceptions of time? Is time the measure of change, a fundamental dimension, entropy's arrow, consciousness construct, or something else entirely? The answer may be that time is all of these things simultaneously, different aspects of a deeper reality that our minds struggle to grasp in its totality. Consider an analogy. A river can be described as flowing water, as a channel carved through landscape, as an ecosystem supporting countless forms of life. as a source of hydroelectric power, as a transportation route, or as a sacred site with cultural significance. None of these descriptions is wrong, but none alone captures the river's complete reality. Similarly, time may be a multifaceted phenomenon that appears different depending on the perspective from which we examine it. The question of whether we can escape time may therefore depend on which aspect of time we are trying to escape. Can we escape time as change? Only by achieving perfect stillness, which may be impossible in a quantum universe, where uncertainty ensures constant fluctuation. Can we escape time as dimension? This might require somehow stepping outside the four-dimensional space-time that appears to contain all physical reality. Can we escape time as entropy's arrow? Perhaps if we could reverse the universal tendency toward disorder, though this would violate fundamental thermodynamic principles. Can we escape time as conscious experience? This seems more promising, given the flexibility we observe in altered states of consciousness, dreams, and meditative experiences. But would such subjective timelessness constitute true escape from time, or merely a change in how we perceive it? As we embark on our exploration of these questions, we must keep in mind that the nature of time itself continues to evolve as our scientific understanding deepens. Quantum mechanics has revealed aspects of reality that seem to transcend classical notions of temporal order. Cosmology has suggested that time itself may have had a beginning and might someday end. The emerging field of quantum gravity hints that space and time themselves might be emergent properties of some deeper, timeless reality. The journey ahead will take us through the strange landscapes revealed by Einstein's relativity, where time stretches and contracts with motion and gravity. We will explore the thermodynamic arrow that gives time its direction, and investigate the quantum mechanical puzzles that suggest reality might be fundamentally timeless at its deepest level. We will examine the possibility that consciousness might offer a pathway to transcendence and consider whether cosmic scenarios might allow escape from temporal imprisonment. But our journey begins with a crucial insight. Time, as we commonly understand it, may not be the fundamental feature of reality we assume it to be. If time is emergent, constructed, or illusory in some deep sense, then the question of escaping it becomes not a matter of fleeing from something real, but of seeing through an illusion to perceive reality's true nature. The prison of time might be one that exists primarily in our minds, built from assumptions about reality that physics is beginning to reveal as incomplete or incorrect. This possibility transforms our quest from an impossible dream of escaping a fundamental feature of reality into a potentially achievable goal of understanding reality more deeply. If time is not what it seems, then neither are the limitations it appears to impose on consciousness and existence. In the chapters that follow, we will see how 20th century physics began to crack the seemingly solid foundation of absolute time, revealing it to be relative, malleable, and perhaps ultimately emergent from timeless quantum processes. Our exploration of whether we can escape time altogether begins with Einstein's revolutionary insight that time, far from being the fixed backdrop against which events unfold, is itself dynamic, relative, and intimately connected to the fabric of space itself. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would forever shatter humanity's understanding of time. Albert Einstein's special theory of relativity didn't just propose a new scientific theory. It revealed that time itself, the seemingly absolute foundation of all existence, was actually relative, flexible, and intimately connected to space in ways no one had ever imagined. Before Einstein, time was considered universal and absolute. Isaac Newton had described time as flowing uniformly throughout the universe, like a cosmic metronome keeping perfect rhythm for all events everywhere. In Newton's vision, if two events happened simultaneously anywhere in the universe, they were simultaneous for all observers, regardless of their motion or location. Time was the unchanging stage upon which the drama of physics played out. Einstein's insight began with a deceptively simple observation about light. Light, he realized, always travels at the same speed in vacuum, regardless of how fast you are moving when you measure it. This seems impossible according to everyday experience. If you throw a ball forward while running, the ball's speed relative to the ground equals your running speed, plus your throwing speed. But light doesn't behave this way. Whether you are standing still or racing toward a light source at tremendous speed, you will always measure light's velocity as exactly 299,792,458 meters per second. This strange behavior of light forced Einstein to a radical conclusion. Since the speed of light is constant for all observers, and since speed equals distance divided by time, something had to give. If light always travels the same speed, but observers in different states of motion measure the same light beam, then distance and time themselves must be flexible, adjusting to preserve light's constant speed. The implications were staggering. Time, Einstein realized, was not absolute, but relative to the observer's motion. Two observers moving at different speeds would literally experience different rates of time passage. This effect, called time dilation, means that time runs slower for objects moving at high speeds relative to stationary observers. Imagine you have an identical twin who embarks on a journey to a nearby star at 90% the speed of light. From your perspective on Earth, your twin's clocks run slow, your twin ages slowly, and all processes aboard the spacecraft unfold in slow motion. A journey that takes 10 years from your Earthbound perspective might subjectively feel like only about 4.5 years to your traveling twin. Upon return, your twin would be significantly younger than you, having literally experienced less time during the journey. This is not science fiction, but established scientific fact, confirmed by countless experiments. Atomic clocks flown on airplanes run slightly slow compared to identical clocks left on the ground. Particles created in cosmic ray collisions high in the atmosphere live longer than they should, allowing them to reach Earth's surface before decaying, because they are moving so fast that time dilation extends their brief lifespans. Even more bizarre is the relativity of simultaneity. Events that are simultaneous for one observer may not be simultaneous for another observer in motion. Imagine two lightning bolts striking the front and rear of a moving train simultaneously, as measured by someone standing on the platform. A passenger aboard the train, moving toward the front lightning bolt and away from the rear one, will see the front bolt strike first because the light from it reaches them sooner. From the passenger's perspective, the lightning strikes are not simultaneous at all. This means there is no universal present moment. The question, what is happening right now on a distant star, has no absolute answer. Different observers, depending on their motion, will disagree about which events at the star are simultaneous with their present moment. The universe does not have a single, shared timeline, but rather a complex web of relative timelines, each valid from its own perspective. Special relativity revealed that space and time are not separate entities, but aspects of a single four-dimensional continuum called space-time. Just as you can rotate an object to view it from different angles, revealing different projections of its three-dimensional shape onto two-dimensional planes, observers in different states of motion see different projections of four-dimensional space-time onto three-dimensional space plus one-dimensional time. What one observer perceives as purely spatial separation, another might perceive as partially temporal separation, and vice versa. Space and time are intimately mixed, with the mixing depending on the observer's motion. This unity of space and time was captured mathematically by Einstein's former teacher, Hermann Minkowski, who declared that henceforth, space by itself and time by itself would fade away into mere shadows, and only their union would preserve an independent reality. 10 years after special relativity, Einstein completed an even more revolutionary theory, general relativity, which revealed that gravity itself is nothing more than the curvature of space-time. Massive objects like stars and planets warp the fabric of space-time around them, and what we experience as gravitational attraction is actually the tendency of objects to follow the straightest possible paths through this curved space-time geometry. General relativity showed that gravity affects time just as motion does. The stronger the gravitational field, the slower time runs. On Earth's surface, time runs slightly slower than it does high above the planet where gravity is weaker. This gravitational time dilation is measurable and must be accounted for in GPS satellites, whose atomic clocks gain about 38 microseconds per day compared to clocks on Earth's surface due to their weaker gravitational environment. Near extremely massive objects like black holes, gravitational time dilation becomes dramatic. At the event horizon of a black hole, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of distant observers. If you watch someone fall toward a black hole, you would see their clock slow down more and more as they approach the event horizon, eventually appearing to freeze at the boundary while their image faded to black. From the falling person's perspective, however, time proceeds normally. They would fall through the event horizon in a finite amount of their own time, experiencing nothing unusual at that moment. The extreme time dilation means that what takes forever from the outside perspective takes only moments from the insider's viewpoint. Time itself becomes stretched to infinity at the black hole's edge. These relativistic effects might seem like exotic curiosities relevant only to extreme situations involving high speeds or strong gravity, but they have profound implications for our understanding of time's nature and the possibility of escaping it. If time is relative and flexible, perhaps it can be manipulated or transcended in ways that absolute time would never allow. Consider the block universe interpretation of relativity, also known as eternalism. If all of space-time exists as a single four-dimensional structure, with past, present, and future equally real, then the flowing present moment we experience is merely a subjective illusion. From this perspective, your birth, your current moment of reading, and your eventual death all exist simultaneously in the block universe, like different locations along a road. The block universe suggests that time travel might be possible, at least in principle. If the past and future exist as real as the present, then perhaps there are pathways through space-time that could allow travel between different temporal locations. Indeed, general relativity does permit certain exotic space-time geometries that contain closed time-like curves, paths through space-time that loop back to earlier times. Kurt Gödel, Einstein's colleague at Princeton, discovered that a rotating universe would contain closed time-like curves, allowing time travel to the past. Frank Tipler showed that an infinitely long, rotating cylinder could create similar temporal loops. Kip Thorne and his colleagues demonstrated that traversable wormholes, hypothetical tunnels connecting distant regions of space-time, could potentially be converted into time machines. However, all of these time travel scenarios require extreme conditions that may not exist in our actual universe. Gödel's solution requires the universe to be rotating, which observations suggest it is not. Tipler cylinders would need to be infinitely long and rotate at nearly the speed of light. Wormhole time machines would require exotic matter with negative energy density to keep the wormhole stable. Moreover, even if such time travel were possible, it would not necessarily constitute escape from time itself. A time traveler would still be following a path through space-time, still embedded within the temporal dimension, just taking an unusual route. The traveler would be manipulating their relationship to time, not stepping outside it entirely. Perhaps more promising for our quest to escape time is the way relativity reveals time's observer-dependent nature. Since there is no absolute simultaneity, no universal present moment, the rigid temporal structure we perceive in everyday life begins to dissolve under closer examination. Different observers slice the block universe into present moments in different ways, none more correct than any other. This relativity of temporal perspective suggests that our ordinary experience of flowing time, of a moving present moment that divides past from future, may indeed be a kind of illusion. If the block universe picture is correct, then all moments are equally real, and the sense of temporal flow is a feature of consciousness rather than physics. Escaping time might therefore be a matter of changing consciousness rather than manipulating physics. Yet even this interpretation faces challenges. While relativity shows that simultaneity is relative for distant events, it preserves a clear temporal order for events along any single world line, the path an object traces through space-time. You cannot use relativity to change the fact that your birth preceded your current reading of these words, which will precede your eventual death. Local temporal sequence remains invariant, even if global simultaneity does not. Furthermore, the block universe interpretation is not the only way to understand relativity. Some physicists and philosophers argue for presentist interpretations that maintain a universal present moment, explaining away the relativity of simultaneity through subtle mechanisms that preserve absolute simultaneity at a fundamental level. Others propose the growing block theory, where the past and present are real, but the future remains unformed. These debates reveal that even Einstein's revolutionary insights did not definitively answer the question of time's ultimate nature. Relativity showed that time is not what Newton thought it was, but exactly what it is remains contentious. Different interpretations of relativistic physics suggest different possibilities for transcending temporal limitations. What relativity did establish beyond doubt is that time is far stranger and more flexible than everyday experience suggests. Time can be stretched, compressed, and mixed with space in ways that would have seemed impossible before 1905. This flexibility hints that time might not be the insurmountable barrier to transcendence it appears to be from our limited perspective. The relativistic revolution also revealed that motion through space affects motion through time. Objects at rest move through time at maximum rate, while objects moving rapidly through space move more slowly through time. This suggests a kind of conservation principle, as if there were a fixed total amount of motion through space-time that could be allocated between spatial and temporal directions. This perspective offers an intriguing way to think about escaping time. If we could somehow redirect all our motion from the temporal direction into spatial directions, might we achieve a kind of timeless existence? Unfortunately, the mathematics of relativity prevents any massive object from redirecting its motion entirely into spatial dimensions. Massive objects always retain some component of motion through time, ensuring they remain embedded within the temporal dimension. Only massless particles like photons can travel entirely through space with no motion through time. From a photon's perspective, if such a perspective can be meaningfully defined, its entire journey from emission to absorption happens instantaneously, regardless of how many billions of years the journey takes from our perspective. Photons exist, in a sense, outside the normal flow of time, experiencing all moments of their existence simultaneously. This raises the tantalizing possibility that consciousness, if it could somehow be separated from massive matter and embodied in pure energy or information, might achieve a photon-like timeless existence. Such speculation ventures far beyond established science, but it illustrates how relativity opens conceptual spaces that were unimaginable in Newton's absolute space-time. Einstein's own attitude toward these implications of his theories was complex. While he accepted the mathematical consequences of relativity, he remained uncomfortable with some of their philosophical implications, particularly the fundamental randomness introduced by quantum mechanics. His famous declaration that God does not play dice with the universe reflected his belief that reality must have a more deterministic, classical character beneath the quantum uncertainties. Regarding time specifically, Einstein seemed to find comfort in the block universe interpretation. When his close friend Michel Besso died, Einstein consoled Besso's family by writing, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." This suggests Einstein viewed the relativistic block universe as revealing time's ultimate unreality, at least as commonly understood. Yet Einstein also recognized that relativity, for all its revolutionary insights, did not provide a complete description of reality. The theory breaks down at the quantum scale and cannot be easily reconciled with quantum mechanics. A complete understanding of time's nature would require a theory of quantum gravity that could unite relativity with quantum mechanics, revealing the deepest laws governing space-time itself. As our exploration continues, we will see how this limitation of relativity opens new avenues for investigating time's nature and the possibility of transcending it. Quantum mechanics introduces elements of fundamental uncertainty and non-locality that seem to challenge even relativistic space-time's reality. The thermodynamic arrow of time that gives temporal direction appears to emerge from statistical mechanics rather than relativistic geometry. But Einstein's revolution established crucial foundations for our quest. Time is not absolute, but relative, not separate from space, but unified with it in space-time, not immune to physical influences, but shaped by motion and gravity. These insights transform the question of escaping time from an obviously impossible fantasy into a subtle problem about the nature of physical law and conscious experience. If time can be dilated, mixed with space, and curved by gravity, then perhaps it can be transcended through sufficiently extreme physical processes or states of consciousness. Relativity does not provide a direct path to temporal escape, but it reveals that time is far more malleable than we once believed. The prison of time, if it exists, has bars that can bend. Einstein's relativity revealed that time is relative and flexible, but it left a profound mystery unsolved. If the fundamental equations of physics treat past and future symmetrically, why does time seem to have a definite direction? Why do we remember the past, but not the future? Why do eggs break, but never spontaneously reassemble? Why does coffee always cool down and never heat up on its own? The answer lies in one of the most profound and counterintuitive concepts in all of physics, entropy, and the second law of thermodynamics. To understand why time has an arrow, we must first understand what entropy means. Entropy is often described as a measure of disorder, but this description, while useful, can be misleading. More precisely, entropy measures the number of microscopic ways a system can be arranged while maintaining the same macroscopic appearance. A system with high entropy can be configured in many different ways at the molecular level, while a system with low entropy has relatively few possible microscopic arrangements. Consider a box divided in half by a removable partition, with all the gas molecules initially confined to the left side. This is a low entropy state because there is essentially only one way to arrange the system, all molecules on the left. When you remove the partition, the molecules spread throughout the entire box, reaching a high entropy state because there are countless ways to arrange the molecules while maintaining the macroscopic appearance of uniform distribution. The second law of thermodynamics states that in isolated systems, entropy tends to increase over time. This is not an absolute rule, but a statistical tendency. In our gas example, it is not impossible for all molecules to spontaneously gather on the left side again, but it is so improbable as to be effectively impossible. The number of ways to arrange molecules uniformly throughout the box vastly exceeds the number of ways to concentrate them all on one side. This statistical behavior gives time its arrow. Low entropy states naturally evolve toward high entropy states, not because of any fundamental asymmetry in the laws of physics, but because there are so many more high entropy states available. The universe moves from unlikely special configurations toward likely generic ones, and this movement defines the direction we call future. The profound puzzle is why the universe started in such an improbably low entropy state in the first place. If we trace cosmic history backward, we find that the early universe was incredibly smooth and uniform, with matter distributed almost perfectly evenly throughout space. This might seem like a high entropy state because of its uniformity, but it was actually extremely low entropy because gravity changes everything. Under the influence of gravity, a smooth, uniform distribution of matter is highly unstable and unlikely. Gravity amplifies tiny fluctuations, causing matter to clump together into increasingly complex structures. The gravitational collapse that forms stars, galaxies, and planetary systems represents an increase in entropy, even though it creates apparent order and complexity. The early universe's smooth distribution was like a pencil balanced perfectly on its tip, a configuration that is possible but extremely unlikely to arise by chance and impossible to maintain for long. Once the pencil starts to fall, it will continue falling until it reaches a stable, high-entropy configuration lying flat on the table. Similarly, once the universe began evolving from its improbably smooth initial state, it continued to evolve toward higher entropy configurations, creating the arrow of time we observe. But why did the universe begin in such a low entropy state? This question touches the deepest mysteries of cosmology and may require us to rethink the nature of time itself. Some cosmologists propose that the universe underwent a period of rapid expansion called cosmic inflation in its earliest moments. During inflation, quantum fluctuations were stretched to cosmic scales, creating the tiny variations in density that would later grow into galaxies and other structures. Inflation might explain how the universe acquired its initial low entropy configuration, but it pushes the mystery back another level. Why did inflation occur, and why did it create a universe with such finely tuned initial conditions? Some theories suggest that inflation is eternal, constantly creating new regions of space with different physical properties. In this eternal inflation scenario, we exist in a region where conditions happen to be suitable for life and observers who can ask questions about time's arrow. Other theories propose that time itself might be emergent from more fundamental, timeless processes. If time arises from the statistical behavior of some underlying reality, then the arrow of time would be built into time's very existence. The universe would not have started in a low entropy state and evolved toward higher entropy. Rather, the statistical processes that create time would necessarily create an entropy gradient that we perceive as temporal direction. The connection between entropy and time becomes even more mysterious when we consider the reversibility of fundamental physics. Newton's laws, Maxwell's equations describing electromagnetism, Schrödinger's equation in quantum mechanics, and Einstein's field equations in general relativity are all time reversible. If you filmed any isolated physical process governed by these laws and played the movie backward, the reverse process would also obey the same laws. Yet our macroscopic world is filled with irreversible processes. Broken eggs do not spontaneously reassemble. Mixed liquids do not spontaneously separate. Living organisms do not spontaneously return to simpler states. This irreversibility emerges from the statistical behavior of vast numbers of particles, not from any fundamental time asymmetry in the underlying physics. The resolution of this apparent paradox lies in understanding that irreversibility is not about individual particles, but about information. When an egg breaks, the information about its initial organized state becomes scattered among countless molecular motions and interactions. In principle, if you could track and reverse the motion of every single molecule involved in the breaking process, you could reassemble the egg. But the information required to perform such a reversal is effectively impossible to gather and process. This connects entropy to information theory in profound ways. The entropy of a system can be understood as the amount of information needed to specify its exact microscopic state, given knowledge of its macroscopic properties. High entropy states require more information to specify completely because there are more possible microscopic configurations consistent with the observed macroscopic state. The famous physicist John Wheeler captured this connection with his phrase "it from bit," suggesting that physical reality might emerge from information rather than information emerging from physical processes. If Wheeler's intuition is correct, then the arrow of time might be fundamentally informational rather than physical, arising from the statistical properties of information processing rather than the dynamics of matter and energy. This informational perspective on time's arrow has fascinating implications for consciousness and the possibility of escaping time. Consciousness appears to be intimately connected to information processing, to the integration and analysis of data from multiple sources into coherent representations of reality. If time's arrow is itself informational, then consciousness might have a special relationship to temporal direction that could potentially be exploited for temporal transcendence. Some theorists have proposed that consciousness might be able to resist or reverse local increases in entropy through sophisticated information processing. Living organisms already do this to some extent, using energy from their environment to maintain complex, low-entropy structures in apparent violation of the second law. Life does not actually violate thermodynamics. It simply exports entropy to its environment while maintaining internal order. But the process demonstrates that local entropy can be decreased through clever information processing. Could consciousness, either biological or artificial, develop the ability to manipulate entropy more dramatically, perhaps even reversing the arrow of time locally? This speculation ventures far beyond established science, but it illustrates how the informational nature of entropy opens conceptual possibilities that would be impossible in a purely mechanical universe. The arrow of time also manifests in quantum mechanics, though in subtler ways than in classical thermodynamics. Quantum measurements appear to be irreversible processes that collapse the wave function from a superposition of multiple states into a single definite outcome. This quantum mechanical arrow of time might be more fundamental than the thermodynamic arrow, arising from the basic structure of quantum theory rather than from statistical mechanics. However, the relationship between quantum mechanics and time's arrow remains controversial. Some interpretations of quantum mechanics, such as the many worlds interpretation, treat wave function collapse as an illusion arising from the branching of parallel universes. In these interpretations, the fundamental quantum evolution is perfectly reversible, and the apparent arrow of time in quantum measurements results from the statistical behavior of information, rather than fundamental physical processes. Other interpretations propose that quantum mechanics itself might be time asymmetric at a fundamental level. The quantum Zeno effect, where frequent measurements can freeze quantum evolution, suggests that observation and time might be connected in deep ways. If consciousness is necessary for wave function collapse, then the arrow of time might be intimately connected to the existence of conscious observers. The cosmic perspective adds another layer to time's arrow. The universe is expanding and cooling, moving from a hot, dense initial state toward a cold, dilute final state. This cosmic evolution provides an additional arrow of time that aligns with the thermodynamic arrow but operates on vastly larger scales. The cosmic microwave background radiation that fills the universe preserves information about conditions when the universe was only 380,000 years old, providing a cosmic fossil record of time's passage. Looking toward the future, cosmologists predict that the universe will continue expanding and cooling until it reaches a state of maximum entropy called heat death. In this far future state, all stars will have burned out, all black holes will have evaporated through Hawking radiation, and the universe will consist of a thin gas of elementary particles at nearly absolute zero temperature. In such a universe, would time still have meaning? Some theorists argue that time itself might end at heat death, since there would be no organized processes to define temporal sequence. Others suggest that even in the heat death era, quantum fluctuations would continue to occur, providing a minimal temporal structure. Still others propose that the universe might be cyclic, with periods of expansion followed by contraction and rebirth, creating an eternal cycle of cosmic time arrows. These extreme scenarios highlight how the arrow of time depends on the existence of organized, complex systems capable of evolving from low entropy to high entropy states. If such systems did not exist, or if they could somehow be made to evolve backward from high entropy to low entropy states, the arrow of time might be weakened or reversed. This suggests another possible avenue for escaping time's arrow. If consciousness could somehow access or create systems that violate the second law of thermodynamics, it might be able to reverse local time's direction. Such systems would need to be powered by some external source of low entropy, but the theoretical possibility exists within the framework of known physics. Maxwell's demon, a thought experiment proposed by James Clerk Maxwell in 1867, illustrates this possibility. The demon is an intelligent being capable of observing individual gas molecules and operating a tiny door between two chambers. By opening the door only for fast molecules moving from left to right and slow molecules moving from right to left, the demon could separate hot and cold gases, apparently violating the second law of thermodynamics. Modern analysis has shown that Maxwell's demon does not actually violate thermodynamics because the information processing required to operate the door generates entropy that more than compensates for the entropy decrease achieved by sorting the molecules. However, this analysis assumes that information processing necessarily generates entropy, an assumption that might not hold for sufficiently advanced forms of computation. Reversible computation, where each computational step can be undone without loss of information, theoretically requires no energy and generates no entropy. If consciousness could be implemented through reversible computation, it might be able to operate a Maxwell's demon-type system without generating compensating entropy, effectively reversing the local arrow of time. Such speculations push far beyond current scientific knowledge, but they illustrate how understanding entropy and time's arrow opens new ways of thinking about temporal transcendence. If the arrow of time is statistical rather than fundamental, if it emerges from information processing rather than basic physical law, then sufficiently sophisticated information processing might be able to manipulate or reverse it. The arrow of time also raises profound questions about free will and determinism. If the future is determined by the past through the statistical evolution of entropy, what role does conscious choice play in shaping events? Some theories propose that consciousness introduces genuine novelty into the universe, creating information that did not exist before and thereby influencing the evolution of entropy. This connects to theories of emergent complexity, where simple rules governing individual particles give rise to complex behaviors at larger scales that cannot be predicted from knowledge of the underlying rules alone. Life, consciousness, and culture might represent forms of emergent complexity that introduce new causal powers into the universe, powers that could potentially influence the direction and strength of time's arrow. As we continue our exploration of whether we can escape time altogether, the arrow of time presents both obstacles and opportunities. The statistical nature of entropy suggests that time's direction is not absolutely fixed, but emerges from the behavior of complex systems. This offers hope that sufficiently advanced consciousness might be able to manipulate temporal direction, at least locally and temporarily. However, the arrow of time also appears to be deeply embedded in the structure of physical law and cosmic evolution. Escaping it completely might require stepping outside the physical universe entirely, or discovering that the universe's apparent physical nature is itself an illusion concealing some deeper, timeless reality. The next stage of our journey will explore the exotic solutions of general relativity that seem to offer loopholes in time structure, paths through space-time that might allow escape from normal temporal flow. But the lessons of entropy and time's arrow will remain relevant, since any viable escape from time must somehow address the statistical foundations that give time its direction in our observed reality. While the arrow of time seems to lock us into forward temporal motion through the statistical march of entropy, Einstein's general relativity contains exotic solutions that appear to offer escape routes from normal temporal flow. These are not merely theoretical curiosities, but mathematically rigorous solutions to Einstein's field equations, describing space-time geometries so extreme that they bend the usual rules of causality and temporal sequence. Yet, as we will discover, these apparent loopholes in time's fabric may not provide the genuine escape from temporality that they initially seem to promise. The most dramatic time distortions occur near black holes, those gravitational monsters where space-time curvature becomes so extreme that not even light can escape. As we learned earlier, time dilation near black holes can stretch temporal intervals to extraordinary degrees, but the full picture is even stranger than simple time slowing. Black holes create regions where the normal relationship between space and time breaks down entirely, where the very concepts of before and after lose their usual meaning. Consider what happens to someone falling toward a black hole. From the perspective of a distant observer, the falling person's time appears to slow down more and more as they approach the event horizon, the black hole's point of no return. At the event horizon itself, time dilation becomes infinite from the outside perspective. The falling person appears frozen at the boundary, their image gradually fading and redshifting until it disappears, while an infinite amount of outside time passes. But from the falling person's perspective, something entirely different occurs. They pass through the event horizon in a finite amount of their own time, experiencing nothing particularly unusual at that moment. Inside the black hole, however, the geometry of space-time becomes so warped that the roles of space and time are reversed. The direction toward the black hole's center becomes time-like rather than space-like, meaning that falling toward the singularity becomes as inevitable as moving forward in time normally is. This reversal suggests a kind of temporal transcendence, where the normal constraints of spatial motion are replaced by temporal inevitability. Yet this is not the escape from time we seek, but rather a different kind of temporal imprisonment. The infalling observer must reach the central singularity in a finite amount of proper time, just as surely as we must move from past to future in normal space-time. The geometry traps them in a temporal flow that leads inexorably toward the singularity, where space-time curvature becomes infinite and physics as we know it breaks down. Even more exotic are the theoretical constructs called closed time-like curves, solutions to Einstein's equations that allow paths through space-time to loop back to earlier times. These represent the most direct challenge to our normal understanding of temporal sequence, creating regions where effect can precede cause, and the past can be influenced by the future. The first such solution was discovered by Kurt Gödel in 1949. Gödel found that in a universe filled with rotating matter, the rotation would drag space-time around with it, creating closed time-like curves that allow time travel to the past. In Gödel's rotating universe, you could theoretically travel in a large circle through space and arrive back at your starting point before you left, creating the possibility of encountering your earlier self. This discovery deeply troubled Einstein, who had not anticipated that his equations would permit such violations of causality. The possibility of closed time-like curves raises the spectre of grandfather paradoxes, where a time traveler could theoretically prevent their own birth by interfering with their grandparents' meeting. Such paradoxes seem to threaten the logical consistency of physical law itself. However, Gödel's solution requires the entire universe to be rotating, and observations indicate that our actual universe shows no net rotation. The cosmic microwave background radiation appears isotropic, meaning it looks the same in all directions, ruling out the large-scale rotation needed for Gödel's time travel mechanism. So while mathematically possible, Gödel's closed time-like curves do not exist in our real cosmos. Other theoretical time travel mechanisms have been proposed that might be more physically realistic. Frank Tipler showed in 1974 that an infinitely long cylinder of matter rotating at nearly the speed of light would create closed time-like curves in its vicinity. Spacecraft could theoretically spiral around such a Tipler cylinder and emerge in their own past, creating another potential time travel scenario. Yet Tipler cylinders face severe practical limitations. They would need to be infinitely long, or at least extremely long, compared to their radius, and would require exotic engineering far beyond any conceivable technology. The rotating cylinder would need to spin at relativistic speeds without flying apart, requiring materials with impossible strength. Like Gödel's rotating universe, Tipler cylinders remain mathematical curiosities rather than practical possibilities. Perhaps the most intriguing time travel scenario involves traversable wormholes, hypothetical tunnels connecting distant regions of space-time. Unlike black holes, which create one-way passages to destruction, wormholes could theoretically allow two-way travel between different locations or times. If one mouth of a wormhole were accelerated to high speed while the other remained stationary, time dilation would cause the two mouths to age at different rates, potentially creating a passage between different temporal epochs. Kip Thorne and his colleagues at Caltech explored this possibility in detail during the 1980s and 90s, investigating whether wormhole time machines could be consistent with known physics. They found that maintaining a traversable wormhole requires exotic matter with negative energy density, something that has never been observed and may not exist in nature. Moreover, attempts to create wormhole time machines appear to trigger instabilities that would destroy the wormhole before time travel becomes possible. Quantum fluctuations in the electromagnetic field would be amplified by the time travel capability, potentially growing strong enough to collapse the wormhole or prevent its formation entirely. The universe seems to have built-in protection mechanisms against violations of causality. These quantum effects suggest a principle that Stephen Hawking called the chronology protection conjecture, the hypothesis that the laws of physics somehow prevent the formation of closed time-like curves that could be accessed by macroscopic objects. While we do not yet have a complete theory of quantum gravity needed to prove this conjecture, the available evidence suggests that nature may indeed prohibit time travel to the past, at least on scales relevant to human experience. Even if closed time-like curves could exist and be accessed, they would not necessarily provide escape from time, in the sense we are seeking. A time traveler following a closed time-like curve would still be embedded within space-time, still following a path through the temporal dimension, just taking an unusual route that loops back to earlier coordinates. The traveler would be manipulating their relationship to time rather than stepping outside temporality altogether. This limitation applies to all the exotic space-time geometries we have discussed. Black hole time dilation, Gödel rotation, Tipler cylinders, and wormhole time machines all involve extreme manipulations of space-time geometry within Einstein's relativistic framework. They stretch, twist and fold the fabric of space-time in extraordinary ways, but they do not provide access to any realm beyond space-time itself. The mathematical structure of general relativity seems to contain space-time as its fundamental arena, with all physical processes embedded within this four-dimensional continuum. Even the most exotic solutions to Einstein's equations describe different ways of organizing space-time, not methods for transcending it entirely. Matter and energy, including any hypothetical conscious beings, remain trapped within the geometric structure that relativity describes. This limitation becomes clearer when we consider what would be required for genuine escape from time. Such escape would presumably involve access to some realm or mode of existence that is genuinely timeless, not merely characterized by unusual temporal relationships. It would require stepping outside the four-dimensional space-time that contains all physical processes, accessing some higher dimensional reality, or fundamentally different type of existence altogether. General relativity, for all its mathematical elegance and empirical success, provides no clear pathway to such transcendence. The theory treats space-time as the fundamental stage upon which physics occurs, not as an emergent phenomenon that might be transcended through deeper understanding. Within the relativistic framework, time remains an inescapable dimension of existence, even when it can be manipulated in exotic ways. Yet the existence of these exotic solutions does reveal something important about time's nature. The fact that relativity permits such extreme temporal effects shows that time is far more flexible and malleable than everyday experience suggests. If space-time can be twisted into configurations that allow time travel, reverse the roles of space and time, or create infinite time dilation, then time cannot be the rigid, absolute framework that pre-relativistic physics assumed. This flexibility suggests that our ordinary conception of time may be limited and incomplete. Just as Newton's absolute time was revealed to be an approximation valid only at low speeds and weak gravity, our current understanding of relativistic space-time might be an approximation of some deeper reality that becomes apparent only under even more extreme conditions. Some theoretical physicists have proposed that space-time itself might be emergent, arising from more fundamental processes that are themselves timeless. In these theories, the four-dimensional space-time of relativity would be like the surface of a lake, a smooth approximation that conceals the complex molecular dynamics underneath. The exotic solutions of general relativity might represent regions where this emergent description begins to break down, revealing hints of the timeless reality beneath. String theory, one of the leading candidates for a theory of quantum gravity, suggests that space-time might indeed be emergent from more fundamental structures. In string theory, the basic constituents of reality are one-dimensional strings vibrating in higher dimensional spaces. The four-dimensional space-time we observe would emerge from the collective behavior of these strings, much as the smooth surface of water emerges from the chaotic motion of countless molecules. If space-time is emergent in this way, then the exotic solutions of general relativity might represent configurations where the emergent description fails, regions where the underlying timeless reality becomes accessible. Black hole singularities, where space-time curvature becomes infinite, might mark the boundaries of space-time's validity as a description of reality. Beyond these boundaries, time itself might cease to be a meaningful concept. Loop quantum gravity, another approach to quantum gravity, suggests even more directly that time might be emergent from timeless quantum processes. In loop quantum gravity, space-time is quantized at the smallest scales, consisting of discrete units of area and volume, rather than the smooth continuum that relativity assumes. Time would emerge from the statistical behavior of these quantum geometric degrees of freedom, much as temperature emerges from the statistical motion of molecules. These quantum gravity theories remain highly speculative and incomplete, but they suggest that the limitations we have identified in relativistic approaches to escaping time might not be fundamental. If time itself is emergent from deeper, timeless processes, then true escape from temporality might be possible through access to these underlying layers of reality. The exotic solutions of general relativity, while not providing direct escape routes from time, may serve as signposts pointing toward regions where our current understanding breaks down and deeper truths become accessible. The singularities inside black holes, the causally paradoxical regions containing closed time-like curves, and the infinite curvatures that appear in cosmological models might all represent boundaries where space-time physics gives way to something more fundamental. This perspective transforms our evaluation of relativity's edge cases from disappointment at their limitations to excitement about their implications. These exotic space-time geometries may not allow escape from time within the relativistic framework, but they reveal that this framework itself has limits. Beyond these limits, new possibilities for temporal transcendence might await discovery. The journey toward understanding whether we can escape time altogether must therefore move beyond classical general relativity to explore the quantum mechanical foundations that may underlie space-time itself. If time is emergent from quantum processes, then quantum mechanics might provide the key to temporal transcendence that relativity alone cannot offer. As we turn our attention to quantum mechanics and its relationship to time, we carry with us the insights gained from exploring relativity's exotic solutions. Time is not rigid but flexible, not absolute but relative, not immune to physical manipulation, but subject to extreme distortion under appropriate conditions. These revelations prepare us to consider even more radical possibilities, that time itself might be an illusion, concealing a deeper, timeless quantum reality that could potentially be accessed through sufficiently profound understanding of nature's fundamental laws. While relativity revealed time's flexibility and pointed toward exotic loopholes in space-time's fabric, quantum mechanics suggests something even more radical, that time might not be fundamental to reality at all. In the deepest formulations of quantum theory, time appears not as a dynamic quantity that can be measured and manipulated like position or momentum, but as a fixed background parameter against which quantum evolution unfolds. This peculiar status of time in quantum mechanics has led some physicists to propose that time itself might be emergent, arising from more fundamental timeless quantum processes that could potentially be transcended through deeper understanding. The strangeness of time in quantum mechanics becomes apparent when we examine the theory's mathematical structure. In classical physics, time and space are treated symmetrically. You can measure both your position and the time at which you occupy that position. You can have uncertainties in both spatial and temporal measurements. But quantum mechanics treats time and space very differently. In quantum theory, spatial coordinates correspond to observable quantities that can be measured and have associated uncertainty principles. You cannot simultaneously know a particle's exact position and momentum as expressed in Heisenberg's uncertainty principle. But time is not treated as an observable in this sense. Instead, time appears as an external parameter that labels when quantum measurements occur, rather than something that can itself be quantum mechanically uncertain. This asymmetric treatment of time creates what physicists call the problem of time in quantum mechanics. If everything else in the universe is subject to quantum uncertainty and superposition, why should time be exempt? The absence of a quantum mechanical time operator suggests that time might not be a fundamental feature of quantum reality, but rather something imposed from outside the quantum description. The implications become even more dramatic when we consider quantum gravity, where general relativity's curved space-time must somehow be reconciled with quantum mechanics. The Wheeler-DeWitt equation, which attempts to describe the quantum mechanics of the universe as a whole, contains no time parameter at all. This equation treats the entire universe as a single quantum system, And remarkably, such a system has no external clock against which its evolution can be measured. The Wheeler-DeWitt equation suggests that the universe as a whole might exist in a timeless quantum state, with time emerging only when we consider subsystems within the universe. From this perspective, the flow of time that we experience would be like the surface currents on a deep ocean, visible patterns that emerge from underlying dynamics but not fundamental features of the water itself. This timeless view of quantum cosmology leads to what physicists call the problem of time, not just the technical issue of how to include time in quantum mechanics, but the deeper conceptual puzzle of how temporal experience can emerge from timeless quantum foundations. If the fundamental description of reality contains no time, how do we explain the vivid temporal experiences that characterize conscious existence? One proposed solution is the Page-Wouters mechanism, named after physicists Don Page and William Wouters, who developed it in 1983. This mechanism shows how the appearance of time evolution can emerge from the correlations between different parts of a timeless quantum system. Even though the total system remains static in a timeless superposition, subsystems within it can appear to evolve relative to each other, creating the illusion of temporal flow. Imagine a quantum system consisting of a clock and another object whose properties you want to track over time. In the Page-Wouters picture, the total system exists in a superposition of all possible clock readings, correlated with all possible states of the object. No time passes for the total system, which remains frozen in this superposition. But if you are part of the system and measure your local clock, you will find it showing a definite time, and the object will appear to have definite properties corresponding to that time. As you continue to measure your clock at later readings, you will observe the object evolving through different states, creating the subjective experience of temporal flow. Yet from the perspective of the total system, no time has passed. The appearance of evolution emerges from the way information is accessed within the timeless quantum superposition, not from any actual temporal development. This mechanism suggests that consciousness itself might play a crucial role in creating temporal experience. If the Page-Wouters mechanism is correct, then time exists only from the perspective of observers embedded within quantum systems, not as an objective feature of reality itself. This opens the tantalizing possibility that sufficiently sophisticated consciousness might be able to manipulate or transcend the mechanisms that create temporal experience. Consider what might happen if consciousness could somehow access the timeless level of quantum reality directly, bypassing the correlations that create the appearance of temporal flow. Such access might allow experience of the eternal quantum superposition that underlies temporal appearances, providing genuine escape from time's limitations. While such speculation ventures far beyond established science, it illustrates how quantum mechanics opens conceptual spaces that classical physics could never accommodate. The quantum measurement process itself raises additional puzzles about time's nature. When a quantum system is measured, its wave function appears to collapse instantaneously from a superposition of multiple states to a single definite outcome. This collapse seems to happen outside the normal flow of time, as an instantaneous event that does not take any finite duration to complete. Some interpretations of quantum mechanics treat wave function collapse as a fundamental physical process that introduces genuine novelty into the universe. Each measurement creates new information that did not exist before, potentially providing the seeds of temporal asymmetry and the arrow of time. From this perspective, consciousness might play an active role in creating time through the act of observation and measurement. Other interpretations, such as the many worlds interpretation, deny that wave function collapse occurs at all. Instead, they propose that all possible measurement outcomes occur in parallel universes that branch off from each quantum measurement. In the many worlds picture, the fundamental quantum evolution is perfectly reversible and timeless, with the appearance of temporal flow arising from the branching structure of parallel realities. If the many worlds interpretation is correct, then escape from time might involve accessing the timeless level, where all possible histories coexist simultaneously. Instead of being trapped within a single temporal trajectory, consciousness might theoretically be able to navigate between parallel timelines or experience multiple temporal sequences simultaneously. Such possibilities stretch the imagination, but they follow naturally from taking quantum mechanics seriously as a description of reality's fundamental nature. Even more radical possibilities emerge from quantum field theory, where particles are understood as excitations in underlying quantum fields that fill all of space. In quantum field theory, the vacuum state, the lowest energy configuration of the fields, is not empty space, but a seething sea of virtual particles constantly appearing and disappearing on timescales too brief for direct observation. These virtual particles exist in a quantum limbo between existence and non-existence, popping into reality for infinitesimal moments before vanishing back into the vacuum. They suggest that even empty space is alive with quantum activity that transcends normal temporal categories. Virtual particles do not follow classical trajectories through space-time, but exist in quantum superpositions that blur the distinction between past, present, and future. Some theorists have proposed that consciousness might be able to access or influence these quantum vacuum fluctuations, potentially manipulating the substrate from which space-time itself emerges. If space and time are built from the quantum interactions of virtual particles, then control over these interactions might allow direct manipulation of temporal structure, or even escape from temporality altogether. The phenomenon of quantum entanglement adds another layer to these speculations. When particles become entangled, their properties remain correlated regardless of the distance separating them, creating what Einstein called spooky action at a distance. Measurements on one entangled particle instantly affect the properties of its partner, even if they are separated by vast distances. This instantaneous correlation suggests that entangled particles exist in a kind of timeless connection that transcends normal spatial and temporal relationships. The entangled state exists as a single quantum entity distributed across space, not as separate objects connected by signals traveling at finite speed. This non-local character of quantum entanglement hints at levels of reality that operate outside normal space-time constraints. If consciousness could somehow become entangled with quantum systems in sophisticated ways, it might be able to access this non-local level of reality directly. Such entanglement might allow experience that transcends normal temporal limitations, providing access to information and influences that exist outside the usual causal structure of space-time. Recent developments in quantum information theory have revealed even more startling connections between quantum mechanics and time. The quantum Zeno effect shows that frequent measurements can freeze quantum evolution, effectively stopping time for quantum systems by preventing them from evolving into different states. This suggests that observation and measurement have the power to directly influence the flow of time at quantum scales. Other quantum information phenomena, such as quantum teleportation and quantum computation, demonstrate ways that information can be manipulated outside normal temporal constraints. Quantum computers can perform certain calculations exponentially faster than classical computers by exploiting quantum superposition and entanglement to explore multiple computational paths simultaneously. If consciousness is fundamentally informational in nature, as some theories suggest, then the quantum information processing capabilities demonstrated in these experiments might be relevant to temporal transcendence. A sufficiently advanced quantum consciousness might be able to process information in ways that transcend normal temporal limitations, potentially accessing past and future states simultaneously, or navigating between different temporal trajectories. The emerging field of quantum biology has revealed that quantum effects play important roles in biological processes that were previously thought to be purely classical. Photosynthesis, bird navigation, and possibly even consciousness itself appear to exploit quantum coherence and entanglement to achieve efficiencies impossible through classical mechanisms alone. These discoveries suggest that the boundary between quantum and classical worlds is not as sharp as once believed. Living systems appear to have evolved ways to harness quantum effects at warm temperatures and in noisy environments where quantum coherence was thought impossible to maintain. If biological consciousness already exploits quantum effects, then the quantum approaches to temporal transcendence we have discussed might not be as far-fetched as they initially appear. However, we must also acknowledge the severe limitations that quantum mechanics places on some forms of temporal manipulation. The no-cloning theorem prohibits perfect copying of unknown quantum states, which would prevent certain types of temporal loops that require identical information to be present at multiple times. The uncertainty principle limits the precision with which temporal relationships can be controlled. Quantum decoherence causes quantum effects to vanish rapidly in warm, noisy environments like those found in biological systems. These limitations suggest that if quantum mechanics provides pathways to temporal transcendence, they would likely be subtle and difficult to access rather than dramatic and obvious. Quantum escape from time, if possible at all, might require extraordinarily sophisticated understanding and control of quantum systems, under conditions far removed from everyday experience. The interpretation of quantum mechanics remains hotly debated, with different interpretations suggesting very different possibilities for temporal transcendence. The Copenhagen interpretation treats wave function collapse as fundamental, suggesting that consciousness plays an active role in creating reality. The many worlds interpretation treats all possibilities as equally real, suggesting that escape from time might involve accessing parallel timelines. Hidden variable theories propose that quantum randomness conceals deeper deterministic processes that might be manipulated for temporal control. Until we have a complete theory of quantum gravity that unifies quantum mechanics with general relativity, these interpretational questions remain open. Such a theory might reveal that both quantum mechanics and general relativity are approximations of some deeper reality that is neither quantum nor relativistic in the conventional sense. This deeper reality might operate according to principles that allow genuine transcendence of temporal limitations. The quest to understand quantum mechanics and its relationship to time continues to push the boundaries of human knowledge and imagination. Whether quantum mechanics ultimately provides pathways to temporal escape or merely reveals new aspects of temporal imprisonment remains to be determined. But the theory has already shown that reality at its deepest level is far stranger and more flexible than classical physics ever suggested. As we continue our exploration of whether we can escape time altogether, the quantum perspective adds new dimensions to our quest. Time might not be fundamental but emergent, not absolute but observer-dependent, not classical but quantum in nature. These possibilities transform the question of temporal escape from a problem in engineering exotic space-time geometries to a challenge in understanding and manipulating the quantum foundations of reality itself. Our journey next turns to consciousness and its relationship to time, exploring whether the subjective experience of temporality might provide keys to transcendence that physics alone cannot offer. The quantum mechanical insights we have explored suggest that consciousness might play a more active role in creating temporal experience than classical physics assumed, opening new avenues for investigation that bridge the gap between objective physical processes and subjective conscious experience. If physics has shown us that time is more malleable and potentially emergent than we once believed, perhaps the answer to escaping time lies not in manipulating external reality, but in understanding the nature of consciousness itself. After all, time as we experience it is fundamentally a conscious phenomenon. We do not observe time directly, but rather construct temporal experience from the flow of sensations, thoughts, and memories through awareness. This subjective dimension of temporality opens possibilities for transcendence that purely physical approaches might miss. The relationship between consciousness and time is intimate and complex. Every moment of conscious experience occurs within a temporal framework that seems to give meaning and structure to awareness itself. You remember the past, experience the present, and anticipate the future through conscious processes that appear to be inherently temporal. Yet this same consciousness that seems trapped within time also demonstrates remarkable abilities to manipulate temporal experience in ways that hint at deeper possibilities for transcendence. Consider the extraordinary flexibility of temporal experience in different states of consciousness. In dreams, you might experience hours or days of subjective time during minutes of REM sleep. Under anesthesia, hours of surgery pass in what feels like an instant, with no subjective temporal experience bridging the transition from consciousness to unconsciousness. During intense focus or flow states, hours can pass like minutes, while boredom can stretch minutes into subjective eternities. These variations in temporal experience suggest that consciousness does not simply observe time, but actively constructs temporal experience from more basic cognitive processes. Neuroscience has revealed that the brain's sense of time emerges from the interaction of multiple neural systems, each tracking different aspects of temporal experience. Your cerebellum times precise motor movements. Your hippocampus creates episodic memories that provide temporal context, and your prefrontal cortex enables planning and temporal reasoning. This distributed nature of temporal processing suggests that consciousness might be able to manipulate temporal experience more dramatically than ordinary states of awareness typically allow. If time perception is constructed rather than directly observed, then perhaps consciousness could be trained or modified to construct radically different temporal experiences, possibly including experiences that transcend normal temporal limitations entirely. Meditation traditions from around the world have long claimed to offer methods for achieving timeless states of consciousness. Advanced practitioners describe entering states of awareness where the normal sense of temporal flow disappears entirely, replaced by experiences of eternal presence that seem to exist outside ordinary time. These contemplative traditions suggest that consciousness naturally possesses capacities for temporal transcendence that are normally obscured by everyday mental activities. The phenomenology of deep meditative states offers tantalizing hints about the relationship between consciousness and time. Experienced meditators report entering absorption states called samadhi, where hours pass in what feels like moments, or conversely, where brief periods contain vast expanses of inner experience. In the deeper states, practitioners describe the complete cessation of temporal awareness, moments of pure consciousness that seem to exist outside the normal flow of time altogether. These reports are remarkably consistent across different contemplative traditions and historical periods. Hindu and Buddhist texts describe states of consciousness where the sense of duration vanishes and awareness rests in timeless presence. Christian mystics write about experiences of eternal now that transcend temporal sequence. Islamic Sufis describe fana, states of ego dissolution, where individual consciousness merges with timeless divine awareness. While such experiences are subjective and difficult to study scientifically, modern neuroscience is beginning to reveal their neurological basis. Brain imaging studies of experienced meditators show dramatic changes in neural activity during deep contemplative states. The default mode network, which is associated with self-referential thinking and temporal projection, becomes less active. Areas involved in attention and present moment awareness show increased activity and coherence. These neurological changes suggest that contemplative practices might actually alter the brain mechanisms responsible for constructing temporal experience. If the sense of time emerges from specific patterns of neural activity, then training consciousness through meditation might allow direct manipulation of these patterns, potentially achieving genuine modifications of temporal experience rather than mere changes in subjective perception. The neuroscience of temporal perception reveals that our sense of time's flow depends on the brain's ability to integrate information across different timescales. The present moment, as experienced by consciousness, is not an instantaneous point, but an extended period lasting roughly 2 to 3 seconds, during which the brain binds together sensory information, memories, and predictions into coherent conscious experiences. This temporal binding process is what creates the sense of flowing time, of moments succeeding one another in seamless progression. But this binding is an active construction that requires ongoing neural work. If consciousness could somehow step outside this binding process, it might access forms of awareness that transcend the normal temporal structure of experience. Some researchers have proposed that consciousness might naturally operate at multiple temporal scales simultaneously. While ordinary awareness focuses on the 2 to 3 second present moment created by temporal binding, consciousness might also have access to much longer temporal scales that integrate information across minutes, hours, or even longer periods. Advanced contemplative states might represent access to these normally unconscious temporal scales. Psychedelic experiences provide another window into consciousness's relationship with time. Substances like LSD, psilocybin, and DMT can profoundly alter temporal perception, creating experiences where normal chronological sequence breaks down entirely. Users report experiencing past, present, and future simultaneously, or accessing states of consciousness that seem to exist outside time altogether. Recent neuroscientific research on psychedelics has revealed that these substances work primarily by disrupting the default mode network and increasing communication between normally separate brain regions. This neural disinhibition might temporarily disable the mechanisms that ordinarily constrain consciousness to normal temporal experience, allowing access to forms of awareness that transcend conventional time. However, both meditative and psychedelic approaches to temporal transcendence face a crucial limitation. Even if these practices can induce genuine states of timeless consciousness, such states remain embedded within the larger temporal framework of physical existence. The meditator still ages during meditation, the psychedelic experience still occurs within a specific time frame, and ordinary temporal consciousness typically returns when the altered state ends. This limitation raises the question of whether subjective timelessness constitutes genuine escape from time, or merely a change in how consciousness relates to temporality. If consciousness can experience timeless states while the brain and body continue to exist within physical time, has consciousness truly transcended temporality, or simply created the illusion of transcendence? Some philosophical traditions argue for a more radical interpretation. They propose that consciousness itself might be fundamentally timeless, with temporal experience arising only when consciousness becomes identified with temporal objects like thoughts, sensations, and memories. From this perspective, the goal is not to achieve timeless states, but to recognize the timeless nature of consciousness itself. Advaita Vedanta, a non-dualistic school of Hindu philosophy, teaches that pure consciousness is eternal and unchanging, beyond the modifications of time and change. What we ordinarily take to be consciousness, the stream of thoughts and experiences that constitute personal identity, is seen as a temporary limitation of this timeless awareness. Liberation involves recognizing one's true nature as this timeless consciousness rather than the temporal ego. Similar teachings appear in other non-dualistic traditions. Dzogchen Buddhism speaks of Rigpa, primordial awareness that exists before the arising of temporal thought. Zen Buddhism points to Buddha nature, the timeless essence of mind that exists prior to conceptual elaboration. Christian mysticism describes the eternal soul that participates in divine timelessness while temporarily embodied in temporal existence. These traditions suggest that escape from time does not require achieving special states of consciousness, but rather recognizing what consciousness already is beneath the temporal modifications that ordinarily capture attention. If this teaching is correct, then temporal transcendence might be immediately available to anyone willing to investigate the nature of awareness itself, rather than requiring years of meditation practice or exotic technologies. However, the relationship between these contemplative insights and scientific understanding of consciousness remains unclear. Neuroscience suggests that consciousness emerges from complex patterns of neural activity that are clearly embedded within physical time. The brain processes that create conscious experience unfold through temporal sequences of neural firing that cannot be separated from the biological timeline of the organism. This creates a puzzle for any theory of timeless consciousness. If consciousness depends on temporal brain processes, how can it be fundamentally timeless? Several possibilities present themselves, each with different implications for the possibility of escaping time through consciousness. One possibility is that consciousness is indeed produced by temporal brain processes, but that these processes can access information or states that transcend their own temporal limitations. Just as a classical computer can simulate timeless mathematical objects despite being built from temporal components, consciousness might be able to represent or experience timeless states despite emerging from temporal neural activity. Another possibility is that consciousness is more fundamental than neuroscience assumes, with brain activity serving as a kind of interface or antenna rather than the generator of conscious experience. If consciousness exists independently of the brain, it might naturally possess timeless characteristics that become apparent when the brain's temporal constraints are relaxed through meditation, psychedelics, or other means. A third possibility is that the hard problem of consciousness, the mystery of how subjective experience arises from objective physical processes, points to limitations in our current scientific worldview. Perhaps consciousness cannot be fully explained in terms of temporal physical processes, because it operates according to principles that transcend the physical framework within which science currently operates. The emerging field of consciousness studies is beginning to address these questions through both theoretical investigation and empirical research. Studies of meditation, psychedelics, and altered states of consciousness are revealing the neural correlates of different forms of temporal experience. Theoretical work on the nature of consciousness is exploring how subjective experience might relate to objective physical processes. Some researchers have proposed that consciousness might be a fundamental feature of reality rather than an emergent property of complex systems. Integrated information theory suggests that consciousness corresponds to integrated information in physical systems, potentially existing at all scales from individual neurons to entire brains to possibly larger systems. If consciousness is indeed fundamental, it might possess characteristics that transcend the temporal limitations of the particular physical systems through which it manifests. This could provide a scientific foundation for contemplative claims about timeless awareness, suggesting that temporal transcendence through consciousness might be more than subjective illusion. The possibility of artificial consciousness adds another dimension to these considerations. If consciousness can be implemented in artificial systems, it might be possible to design forms of artificial awareness that have different relationships to time than biological consciousness possesses. Computer systems already demonstrate forms of information processing that transcend human temporal limitations, accessing databases instantly and performing calculations at speeds impossible for biological cognition. An artificial consciousness designed with different temporal architecture might be able to experience multiple time streams simultaneously, access information from across extended temporal periods, or operate according to temporal principles entirely different from those that constrain biological awareness. Such systems might provide practical pathways to temporal transcendence that complement the contemplative approaches developed by human traditions. However, the development of artificial consciousness also raises questions about the relationship between information processing and genuine conscious experience. Even if artificial systems can manipulate temporal information in sophisticated ways, would they necessarily possess the subjective dimension of experience that seems central to consciousness? The question of artificial consciousness remains hotly debated, with profound implications for understanding consciousness and its relationship to time. As we consider the possibility of escaping time through consciousness, we must acknowledge both the promising evidence and the significant limitations. Contemplative traditions offer compelling reports of timeless awareness. Neuroscience reveals the constructed nature of temporal experience, and altered states demonstrate consciousness's capacity for temporal flexibility. Yet these phenomena might represent changes in how consciousness relates to time, rather than genuine escape from temporality. The quest for temporal transcendence through consciousness may ultimately depend on resolving deeper questions about the nature of consciousness itself. Is awareness fundamentally temporal or timeless? Does consciousness emerge from physical processes or represent a more fundamental aspect of reality? Can subjective experience transcend the temporal limitations of its physical substrate? These questions point beyond consciousness studies toward even grander cosmological considerations. If consciousness is fundamental to reality, then understanding its relationship to time might require understanding the relationship between mind and cosmos at the larger scales. Our journey continues by exploring how cosmology and theories of multiple universes might provide contexts within which consciousness could achieve genuine temporal transcendence. While consciousness offers intriguing possibilities for temporal transcendence through altered states of awareness, cosmology opens even more radical vistas by suggesting that time itself might be a local rather than universal phenomenon. Modern theories of the universe's origin, evolution, and ultimate fate reveal scenarios where our familiar temporal framework dissolves into something far stranger and more flexible. These cosmological perspectives suggest that escape from time might not require exotic physics or advanced consciousness techniques, but rather a shift in perspective to recognize that we already exist within a reality where timelessness is more fundamental than temporality. The most profound challenge to universal time comes from our understanding of the universe's beginning. The Big Bang Theory describes how our observable universe expanded from an extremely hot, dense initial state approximately 13.8 billion years ago. But what came before the Big Bang? This question probes the very foundations of temporal existence, since it asks about a time before time itself began. Classical Big Bang cosmology suggests that time and space emerged together at the moment of cosmic birth. Before this moment, the concepts of before and after become meaningless because time itself did not exist. This is not simply a matter of lacking information about earlier epochs, but a more fundamental limitation where the concept of earlier becomes logically incoherent. Time appears to have an absolute beginning, before which lies not empty time, but the absence of temporality altogether. Yet this picture has been dramatically complicated by the theory of cosmic inflation, which proposes that the universe underwent a period of exponential expansion in its earliest moments. Inflation was originally conceived to solve certain puzzles about the universe's observed properties, such as why the cosmic microwave background radiation appears so uniform across regions that seem too distant to have been in causal contact. But inflation theory has evolved to suggest something much more radical than a brief period of rapid expansion in our universe's early history. Eternal inflation models propose that inflation is an ongoing process that never completely ends. While inflation stops in some regions, allowing normal matter and energy to form galaxies and stars, it continues in other regions, constantly creating new volumes of space that undergo their own inflationary expansion. This eternal inflation creates what cosmologists call the multiverse, an infinite collection of bubble universes separated by eternally inflating space. Each bubble universe, including our own, represents a region where inflation ended and normal physics took over. But the larger multiverse contains infinitely many such bubbles, each with potentially different physical laws and cosmic histories. From the perspective of eternal inflation, our entire observable universe, with its 13.8 billion year history, is just a tiny bubble floating in an infinite sea of inflating space-time. The multiverse as a whole has no beginning and no end, existing in a kind of eternal present, where new universes are constantly being born, while older ones evolve and eventually die. This multiverse perspective fundamentally challenges our concept of cosmic time. While each bubble universe has its own internal timeline, there is no universal clock that measures time for the multiverse as a whole. Different regions of the multiverse experience different temporal flows, and the concept of simultaneity becomes meaningless when applied to widely separated bubble universes. The implications for escaping time are profound. If consciousness could somehow access the level of reality corresponding to the eternally inflating multiverse, it might transcend the temporal limitations of any particular bubble universe. Instead of being trapped within the 13.8 billion year timeline of our cosmic bubble, awareness might access the timeless perspective from which all bubble universes appear as temporary fluctuations in an eternal substrate. But how might such access be achieved? Some speculative theories suggest that information or even consciousness might be able to traverse the boundaries between bubble universes under extreme conditions. If bubble universes can collide or merge, as some models predict, such cosmic catastrophes might create windows through which conscious beings could access the larger multiverse structure. Other theories propose that consciousness might naturally operate at scales that transcend individual bubble universes. If awareness is somehow fundamental to reality rather than merely emergent from complex matter arrangements, it might exist at the level of the multiverse itself, rather than being confined to particular cosmic bubbles. From this perspective, our ordinary experience of being embedded within a specific timeline would be an illusion arising from limited identification with local rather than cosmic consciousness. Even more radical possibilities emerge from quantum cosmology, which applies quantum mechanics to the universe as a whole. In quantum mechanics, systems can exist in superpositions of multiple states until measurement forces them to collapse into definite outcomes. Applied to cosmology, this suggests that the universe might exist in superpositions of different possible histories, with our observed timeline representing just one branch of a vast quantum multiverse. The many worlds interpretation of quantum mechanics, when extended to cosmology, suggests that every quantum event causes the universe to split into multiple parallel branches, each corresponding to a different possible outcome. This creates an ever-branching tree of parallel universes, all equally real but causally isolated from each other after the branching events occur. If this picture is correct, then consciousness might naturally exist across multiple parallel timelines simultaneously, with our ordinary awareness representing only a tiny fraction of our total existence. Escape from time might involve expanding consciousness to encompass multiple parallel timelines, experiencing the full quantum multiverse rather than just the single temporal thread that normally captures attention. Some interpretations of quantum cosmology go even further, suggesting that time itself emerges from the statistics of quantum branching rather than being fundamental to reality. In these models, the multiverse exists as a timeless quantum superposition, with temporal experience arising only from the perspective of observers embedded within particular branches of the universal wave function. This connects to the quantum mechanical approaches to timelessness we explored earlier, but extends them to cosmic scales. Instead of individual quantum systems existing in timeless superpositions that create apparent temporal evolution through correlations, the entire multiverse might exist in a cosmic superposition that creates the illusion of universal temporal evolution through the statistics of quantum branching. These quantum cosmological models suggest that our entire cosmic timeline, from the Big Bang to the heat death of the universe, might be like a single frame in an infinite movie that exists all at once in the timeless quantum multiverse. Consciousness embedded within such a frame would experience temporal flow as it processes information sequentially, but the fuller reality would be timeless and eternal. The cyclic universe models offer yet another perspective on cosmic temporality. Instead of having a single beginning and end, these models propose that the universe undergoes infinite cycles of expansion and contraction, birth and death, with each cycle potentially lasting hundreds of billions of years. In cyclic cosmology, our current expanding phase will eventually reverse into contraction, leading to a big crunch that serves as the Big Bang of the next cycle. From the perspective of cyclic cosmology, time becomes circular rather than linear, with cosmic history repeating endlessly through infinite cycles. This cyclical view of time appears in many ancient philosophical and religious traditions, from Hindu concepts of cosmic cycles to Nietzschean ideas of eternal recurrence. If cyclic cosmology is correct, then consciousness might naturally transcend the limitations of any particular cosmic cycle by recognizing its participation in eternal cosmic rhythms. Some versions of cyclic cosmology propose that information or even conscious beings might survive the transition between cosmic cycles, carrying forward experiences and knowledge from previous universes into new cosmic epochs. This opens the possibility of truly eternal consciousness that transcends not just individual lifetimes, but entire cosmic histories, accumulating experience and wisdom across infinite universal cycles. The ekpyrotic scenario, developed by theorists including Neil Turok and Paul Steinhardt, offers a particularly elegant version of cyclic cosmology based on string theory and higher dimensional physics. In this model, our three-dimensional universe exists as a membrane, or brain, in higher dimensional space. Cosmic cycles result from collisions between parallel brains that create the appearance of Big Bang and Big Crunch events from our three-dimensional perspective. If consciousness could somehow access the higher dimensional perspective from which brain collisions appear as local events, it might achieve a truly transcendent view of cosmic temporality. Instead of being trapped within the timeline of a particular cosmic cycle, awareness might operate from the higher dimensional space where all cycles appear simultaneously as different configurations of colliding brains. These cosmological scenarios stretch our concepts of time and existence to their breaking points, but they are grounded in serious scientific theories about the universe's fundamental nature. While speculative, they suggest that our ordinary conception of being trapped within a single cosmic timeline might be a severe limitation of perspective rather than an accurate description of a reality's structure. The anthropic principle adds another dimension to these cosmological considerations. This principle observes that the physical constants and laws of our universe appear to be fine-tuned for the existence of stars, planets, and life. Small changes in fundamental constants would result in universes where complexity could never arise, where consciousness could never emerge to ask questions about time and existence. In a multiverse containing bubble universes with different physical laws, the anthropic principle explains this fine-tuning as a selection effect. We necessarily observe a universe compatible with our existence, regardless of how unlikely such universes might be in the larger multiverse. Most bubble universes might be lifeless and unconscious, with observers emerging only in the rare bubbles, where conditions permit complexity and awareness. But this selection effect might also apply to temporal properties. Perhaps consciousness can only emerge in universes with specific temporal structures, where time flows in directions and at rates compatible with information processing and memory formation? If so, then our experience of being embedded within flowing time might reflect the anthropic requirements for consciousness rather than fundamental features of all possible realities. This suggests that escape from time might involve transcending the anthropic selection effects that normally constrain conscious experience to time-compatible universes. If consciousness could somehow access the larger multiverse that includes universes with radically different temporal properties, it might experience forms of existence that transcend our current temporal limitations. The ultimate fate of our universe adds yet another perspective on cosmic temporality. Current observations suggest that cosmic expansion is accelerating, driven by a mysterious dark energy that comprises roughly 70% of the universe's total energy content. If this acceleration continues, our universe will expand forever, cooling and diluting until it reaches a state of maximum entropy known as heat death. In the heat death scenario, all stars will eventually burn out. All black holes will evaporate through Hawking radiation, and the universe will consist of a thin gas of elementary particles at temperatures approaching absolute zero. In such a universe, would time itself come to an end? With no organized processes to mark temporal intervals, no entropy gradients to define time's arrow, the concept of temporal flow might become meaningless. Some theorists argue that consciousness could not survive in a heat-death universe, since the information processing required for awareness would be impossible in the absence of energy gradients. Others propose that sufficiently advanced civilizations might find ways to continue existing even in the far future universe, perhaps by exploiting rare quantum fluctuations or by somehow accessing alternative forms of energy. If consciousness could survive to the heat-death era, it might experience a form of existence radically different from anything possible in our current cosmic epoch. With the normal sources of temporal flow eliminated, conscious experience might become truly timeless, existing in eternal contemplation that transcends the temporal limitations of earlier cosmic eras. The relationship between information and thermodynamics suggests another approach to cosmic temporal transcendence. Information appears to be conserved in quantum mechanics, with the total amount of information in the universe remaining constant, even as it becomes redistributed through physical processes. This conservation of information might provide a pathway for consciousness to survive cosmic evolution, and even transcend normal temporal limitations. If consciousness is fundamentally informational in nature, as some theories propose, then it might naturally participate in the universe's information conservation laws. Instead of being destroyed by cosmic evolution, conscious information might be transformed and redistributed in ways that preserve its essential structure, while allowing it to transcend the temporal limitations of particular physical substrates. These cosmological perspectives on time and consciousness point toward possibilities for temporal transcendence that dwarf anything suggested by individual meditation practices or even exotic physics. If our universe is embedded within an eternal multiverse, if consciousness operates at cosmic scales, if information is conserved across cosmic evolution, then the barriers to escaping time might be far less absolute than they appear from our limited terrestrial perspective. Yet, these cosmic possibilities also highlight how much we still do not understand about the fundamental nature of reality. The theories we have explored remain highly speculative, and even our best established cosmological models contain enormous uncertainties about the universe's ultimate structure and fate. The relationship between consciousness and cosmos remains one of the deepest mysteries in all of science. As our exploration continues, we turn next to even more speculative but potentially transformative possibilities raised by the simulation hypothesis. If our entire reality is computational in nature, then escape from time might involve transcending the computational processes that create temporal experience accessing the hardware and software that implement our simulated existence? What if everything you have ever experienced, every moment of temporal flow, every memory of the past and anticipation of the future, is nothing more than the execution of a computer program? The simulation hypothesis, popularized by philosopher Nick Bostrom, but with roots stretching back to ancient skeptical philosophy, suggests that our entire reality might be a computational simulation running on some vast computer system. If this radical possibility is correct, then the nature of time itself would be fundamentally different from what physics suggests, and escape from temporal limitations might be as simple as hacking the code that creates our simulated existence. The simulation hypothesis emerges from straightforward observations about the exponential growth of computational power and the increasing sophistication of virtual environments. Video games today create immersive worlds with their own physics, geography, and even primitive forms of artificial life. Virtual reality systems can create convincing sensory experiences that temporarily replace our perception of the external world. Computer simulations model everything from weather patterns to galaxy formation with increasing accuracy and detail. If computational power continues to grow according to trends like Moore's law, which predicts the doubling of transistor density every 2 years, future computers might become powerful enough to simulate entire universes down to the quantum level. Such simulations could contain conscious beings who experience their simulated world as completely real, having no access to the external reality where their simulation runs. Bostrom's argument takes this possibility and extends it through statistical reasoning. If advanced civilizations develop the ability to run detailed simulations of their evolutionary history, they might run many such simulations for scientific, entertainment, or other purposes. Each simulation could contain billions of conscious beings who believe themselves to be living in base reality, rather than a computational approximation. In such a scenario, the vast majority of conscious experiences would occur within simulations rather than in base reality. Any randomly selected conscious being would be far more likely to exist within a simulation than in the original physical universe. Since we have no direct access to information about whether we are simulated, the statistical argument suggests we should assign significant probability to the possibility that we ourselves are simulated beings. This statistical reasoning leads to what Bostrom calls the trilemma. Either advanced civilizations almost never develop the computational power needed for detailed ancestor simulations, or they develop such power but choose not to use it for running simulations, or we are very probably living in a computer simulation ourselves. Current trends in computational development make the first option seem unlikely, and the potential scientific and cultural value of ancestor simulations makes the second option questionable, leaving simulation as a genuine possibility that deserves serious consideration. If we are indeed living in a simulation, then the nature of time becomes radically different from what our physical theories suggest. Time in a computer simulation is not a fundamental dimension of reality, but rather the sequence in which computational operations are executed. The computer running our simulation might process our universe's history in real time, faster than real time, slower than real time, or even in non-sequential order, jumping back and forth between different temporal periods as needed. From our perspective within the simulation, we would experience smooth temporal flow, regardless of how the external computer processes our reality. If the simulation were paused for 1,000,000 years and then resumed, we would never notice the interruption because our simulated consciousness would pause as well. If our universe's entire history were computed in reverse order, we would still experience time flowing forward because our memories and perceptions would be computed consistently with that forward flow. This computational perspective on time opens remarkable possibilities for temporal transcendence. If time is merely the order of computational operations rather than a fundamental aspect of reality, then beings with access to the simulation's computational substrate might be able to manipulate temporal experience in ways impossible within normal physics. Consider the possibilities available to programmers or administrators with access to the computer running our simulation. They could pause time, rewind it, fast forward through long periods, or even branch the simulation to explore alternative timelines. They could back up and restore earlier states of the universe, effectively providing a form of cosmic time travel. They could run multiple copies of the same simulation with slight variations, creating parallel versions of history that unfold simultaneously on the same hardware. Even more dramatically, they could extract individual consciousness patterns from the simulation and run them in different computational environments with entirely different temporal properties. A simulated being could be transferred to a virtual environment where subjective time passes much faster or slower than in the original simulation, or to environments where time flows backward, branches into multiple streams, or operates according to entirely novel temporal logics. If consciousness is fundamentally computational, as many theories of mind suggest, then these manipulations would represent genuine alterations of temporal experience rather than mere illusions. The conscious being would actually experience different temporal flows, not just think they were experiencing them. This offers a pathway to temporal transcendence that is both technically feasible, given sufficient computational power, and conceptually clear in its mechanisms. The possibility of nested simulations adds even more layers to these considerations. If we are simulated beings running in a computer, we might ourselves create simulations within our simulated world. These nested simulations could have their own temporal properties, potentially very different from those of the parent simulation. A hierarchy of nested simulations could contain conscious beings experiencing radically different temporal flows, all supported by the same underlying computational hardware. Advanced simulated civilizations might eventually discover their simulated nature and develop the ability to hack their own simulation. This could allow them to modify the computational rules that govern their reality, potentially including the rules that create temporal experience. Simulated beings might learn to pause their local time while continuing to think and act, effectively achieving a form of temporal transcendence within their computational environment. They might also discover ways to communicate with, or even transfer to the higher reality that contains their simulation. If successful, such transfer would represent the ultimate escape from simulated time into whatever temporal framework characterizes the base reality where their simulation runs. This base reality might itself be a simulation nested within an even higher reality, creating an infinite hierarchy of computational realities, with potentially different temporal properties at each level. The technical challenges of implementing universe simulations provide clues about how simulated time might actually work. Creating a convincing simulation of reality requires enormous computational resources, especially if the simulation must include quantum mechanical effects, complex chemistry, and biological processes. Even with exponentially growing computational power, practical limitations would likely force simulation designers to use various optimization techniques. One common optimization is procedural generation, where detailed content is created only when and where it is needed, rather than computing everything in advance. A simulation of Earth might generate detailed terrain only around conscious observers, leaving distant regions in low-resolution states until they become relevant. This suggests that simulated time might also be optimized, with detailed temporal modeling occurring only for events that directly affect conscious experience. Another optimization technique is hierarchical simulation, where different aspects of reality are modeled at different levels of detail depending on their importance. Fundamental physics might be simulated precisely for events that matter to conscious observers, while vast regions of empty space are modeled with simplified approximations. This hierarchical approach might extend to temporal modeling as well, with precise time evolution computed only for events within the immediate experience of simulated consciousness. These computational considerations suggest that simulated time might be fundamentally discrete rather than continuous, composed of individual computational time steps rather than smooth temporal flow. If our simulated reality operates on a discrete temporal grid, then the smallest meaningful unit of time would be the duration of a single computational operation, rather than any fundamental physical constant. This discretization of time offers another avenue for temporal manipulation within simulated realities. Beings with access to the simulation's code might be able to alter the temporal grid spacing, effectively speeding up or slowing down time for particular regions or events. They might be able to insert additional computational time steps between normal operations, creating pockets of extended temporal experience within brief periods of simulated time. The relationship between consciousness and computation in simulated realities raises profound questions about personal identity and temporal continuity. If a simulated being is copied, paused and resumed, or transferred between different computational substrates, in what sense do they maintain identity across these transitions? These questions become particularly acute when considering temporal manipulations that might fragment or duplicate conscious experience across multiple time streams. Some theories of personal identity suggest that consciousness is tied to specific patterns of information processing, rather than to particular physical or computational substrates. If correct, this would mean that simulated beings could maintain identity across radical changes in their computational implementation, including changes that alter their temporal experience. A consciousness could potentially experience multiple parallel timelines simultaneously while maintaining a coherent sense of self. Other theories emphasize the importance of temporal continuity for personal identity, suggesting that beings who experience fragmented or non-linear time might lose coherent selfhood. These theories imply that temporal manipulations in simulated realities could fundamentally alter or even destroy the conscious beings subjected to them, raising ethical questions about the treatment of simulated consciousness. The simulation hypothesis also raises questions about the nature of physical laws and whether they would apply within simulated realities. If our physics emerges from computational rules rather than fundamental properties of reality, then the laws we observe might be artifacts of our particular simulation's programming rather than universal truths. Other simulations might operate according to entirely different physical principles, including different relationships between matter, energy, space, and time. This possibility suggests that escape from our current temporal limitations might not require transcending physical law, but simply transferring to simulations with more favorable temporal physics. A simulated reality might allow faster than light travel, time travel, or even consciousness that operates outside normal temporal constraints entirely. Such possibilities would be limited only by the computational creativity of the simulation's designers. However, the simulation hypothesis faces significant challenges and criticisms that affect its implications for temporal transcendence. The computational requirements for detailed universe simulation appear to be enormous, possibly requiring more computational resources than could be practically assembled even by advanced civilizations. The energy requirements alone might make universe simulation prohibitively expensive. Critics also argue that the simulation hypothesis is unfalsifiable and therefore unscientific. Since any evidence we might gather about our reality's nature would itself be part of the simulation, we could never definitively prove or disprove our simulated status through empirical investigation. This makes the simulation hypothesis more of a philosophical thought experiment than a scientific theory with testable predictions. Furthermore, the assumption that consciousness can be computationally implemented remains highly controversial. While many cognitive scientists and artificial intelligence researchers accept computational theories of mind, others argue that consciousness requires non-computational processes that cannot be simulated on digital computers. If consciousness is not computational, then simulated realities might contain behavioral zombies that act conscious without actually experiencing awareness. These limitations suggest that even if the simulation hypothesis is correct, the pathways to temporal transcendence it suggests might not be practically accessible. Simulated beings might lack the computational resources needed to hack their simulation, or they might discover that their consciousness cannot actually be transferred to different computational environments without losing essential aspects of awareness. Nevertheless, the simulation hypothesis provides a valuable perspective on the nature of time and the possibilities for transcending temporal limitations. Whether or not we are actually simulated, the computational approach to understanding time reveals that temporal experience might be far more malleable than physical theories suggest. If time is information processing rather than fundamental physics, then sufficiently advanced information technologies might indeed provide pathways to temporal transcendence. The growing sophistication of virtual and augmented reality technologies, the development of increasingly powerful artificial intelligence systems, and the emergence of quantum computing all point toward futures where the boundary between simulated and non-simulated reality becomes increasingly blurred. These technological developments might provide practical tools for temporal manipulation, even if we are not living in a simulation ourselves. As our exploration of temporal transcendence approaches its conclusion, the simulation hypothesis serves as a bridge between the exotic physics and cosmic perspectives we have explored, and the practical question of whether escape from time is actually possible within the constraints of known reality. If time is computational, then temporal transcendence becomes an engineering problem rather than a fundamental impossibility. But if time is more deeply embedded in the structure of reality than computation alone can capture, then our quest for escape may require even more radical reconceptualizations of existence itself. Our final chapters will examine these ultimate questions about time's nature and the possibilities for transcendence, drawing together insights from physics, consciousness studies, cosmology, and computation to evaluate whether genuine escape from temporality is possible, or whether the very concept of such escape rests on fundamental misunderstandings about the nature of time and existence. After exploring exotic space-time geometries, quantum timelessness, consciousness studies, cosmic perspectives, and computational scenarios, we must now confront the fundamental question that underlies our entire quest. Does physics, in its deepest and most complete form, actually permit timeless existence? Or are all the possibilities we have explored merely different ways of manipulating our relationship to time without ever truly escaping temporality itself? The answer to this question requires us to examine the most profound foundations of physical reality and consider whether the concept of existence beyond time is coherent within any possible physical framework. The first challenge to timeless existence comes from the apparent universality of temporal processes in physics. Every known physical phenomenon, from particle interactions to cosmic evolution, unfolds through temporal sequences that cannot be eliminated without destroying the phenomenon itself. Even in the block universe interpretation of relativity, where past, present, and future are equally real, events still maintain definite temporal relationships to each other that cannot be arbitrarily rearranged. Consider the decay of a radioactive atom, one of the most precisely understood processes in physics. The atom exists in an unstable state for some period of time, then undergoes decay that transforms it into different particles and energy. This process has a well-defined temporal structure. The initial unstable state precedes the decay event, which precedes the final stable state. While quantum mechanics introduces probabilistic uncertainty about when the decay will occur, it does not eliminate the temporal sequence that defines the decay process itself. Similar temporal structures appear throughout physics. Chemical reactions involve reactants that transform into products through intermediate states that unfold in specific temporal orders. Biological processes like metabolism, reproduction, and evolution require complex temporal coordination between different molecular and cellular events. Even fundamental forces like electromagnetism involve temporal relationships between causes and effects that cannot be eliminated without destroying the physical phenomena they describe. This universality of temporal structure suggests that time might be more deeply embedded in physical reality than our earlier explorations indicated. While relativity showed that time is relative and quantum mechanics hinted that time might be emergent, every actual physical process still requires temporal structure to be coherent. This raises the question of whether truly timeless existence is compatible with any form of physical process whatsoever. The thermodynamic perspective adds another layer of difficulty. As we learned earlier, the second law of thermodynamics gives time its direction through the statistical tendency of entropy to increase. But thermodynamics also suggests that any physical system capable of processing information or maintaining organized structure must operate within temporal frameworks that allow entropy gradients to drive its operation. Living systems provide the clearest examples of this thermodynamic constraint. Biological organisms maintain their complex organization by constantly importing low entropy energy from their environment and exporting high entropy waste products. This process requires temporal structure because it depends on cyclical patterns of energy intake, processing, and waste elimination that must unfold in proper sequence to maintain life. Even hypothetical non-biological forms of information processing appear to face similar constraints. Computer systems require temporal sequences of computational operations to process information effectively. Memory systems need temporal structure to distinguish between storage, retrieval, and updating operations. Any system complex enough to support consciousness would likely require sophisticated temporal coordination between its various information processing components. These considerations suggest that truly timeless existence might be incompatible with any form of organized information processing, including consciousness itself. If consciousness requires temporal structure to function, then timeless existence might necessarily be unconscious existence, a state that would hardly constitute escape from time in any meaningful sense for conscious beings. However, some theoretical frameworks in physics do suggest possibilities for genuinely timeless existence that transcend these limitations. The most promising approaches emerge from attempts to understand the deepest foundations of physical law, where conventional concepts of space, time, matter, and energy begin to break down, and more fundamental structures emerge. String theory, the leading candidate for a theory of quantum gravity, suggests that the familiar four-dimensional spacetime of relativity emerges from more fundamental processes involving vibrating strings in higher dimensional spaces. In some versions of string theory, the dimensions we experience as space and time are emergent properties of string dynamics rather than fundamental aspects of reality itself. If space-time is emergent in this way, then the deepest level of reality described by string theory would exist beyond or before the emergence of temporal structure. This pre-temporal reality might be timeless in a genuine sense, with time appearing only when string configurations reach sufficient complexity to support the emergent space-time that we observe. Consciousness or information patterns that could somehow access this pre-temporal level of string dynamics might experience genuinely timeless existence. Such access would not merely involve manipulating temporal relationships within spacetime, but transcending spacetime altogether to operate at the level of fundamental string processes that create temporal structure as an emergent phenomenon. Loop quantum gravity offers a different but equally radical perspective. In this approach, space and time themselves are quantized, consisting of discrete units that combine to create the smooth spacetime that general relativity describes. At the smallest scales, space consists of discrete loops, and time consists of discrete moments, with smooth temporal flow emerging only at larger scales through statistical averaging. The discrete quantum geometry suggested by loop quantum gravity implies that spacetime itself might be constructed from more fundamental discrete elements that exist in a timeless quantum superposition. Time would emerge from the statistical properties of these quantum geometric degrees of freedom, much as temperature emerges from the statistical motion of molecules. If this picture is correct, then consciousness that could access the timeless quantum superposition underlying spacetime might experience existence beyond the emergent temporal structure that characterizes ordinary reality. Such consciousness would operate at the level where space and time are constructed rather than being embedded within already constructed spacetime. The holographic principle emerging from black hole thermodynamics and string theory suggests an even more radical reimagining of space, time, and information. This principle proposes that all the information contained within any volume of space can be encoded on the boundary of that volume, much as a hologram encodes three-dimensional information on a two-dimensional surface. Applied to cosmology, the holographic principle suggests that our entire three-dimensional universe, with its temporal evolution, might be encoded on a two-dimensional boundary at the edge of space. From this perspective, the temporal flow we experience would be a kind of holographic projection from timeless information encoded on this cosmic boundary. Consciousness that could access the information encoding level rather than the holographic projection might experience timeless existence that contains all temporal possibilities simultaneously. Instead of being embedded within temporal flow, such consciousness would operate from the timeless perspective that generates temporal experience as one of its projections. These quantum gravity approaches suggest that timeless existence might be possible at the deepest foundations of physical reality, but they also highlight the extreme conditions that would be required for such existence. Accessing pretemporal string dynamics, timeless quantum geometry, or holographic encoding would require transcending not just ordinary matter and energy, but the very space-time framework within which all normal physics operates. The practical challenges of achieving such transcendence are staggering. Even if these theoretical frameworks correctly describe reality's foundations, developing technologies or consciousness techniques capable of accessing these foundations would require advances far beyond current scientific knowledge. The energy scales involved in quantum gravity are typically the Planck scale, where quantum effects become dominant in gravitational phenomena, requiring energies about 10 to the 19th power times greater than those accessible in current particle accelerators. Moreover, it remains unclear whether consciousness or any form of organized information could survive the transition to these fundamental levels of reality. The discrete quantum geometry of loop quantum gravity or the pre-temporal dynamics of string theory might be incompatible with the complex information patterns required for consciousness. Attempts to access timeless existence might result in the destruction of consciousness rather than its liberation from temporal constraints. The heat death scenario for the universe's ultimate fate provides another perspective on the possibility of timeless existence within physics. Current observations suggest that cosmic expansion will continue accelerating until the universe reaches maximum entropy. With all stars burned out, all black holes evaporated, and only a thin gas of elementary particles remaining at temperatures approaching absolute zero. In such a heat-death universe, the normal sources of temporal structure would be eliminated. Without energy gradients to drive irreversible processes, without organized systems to mark temporal intervals, the arrow of time might effectively disappear. The universe would reach a state of thermodynamic equilibrium where no further change is possible, creating conditions that might be described as timeless. Some theorists argue that consciousness could not survive in a heat-death universe because the energy required for information processing would no longer be available. Others propose that sufficiently advanced civilizations might find ways to continue existing by exploiting rare quantum fluctuations, or by implementing forms of reversible computation that require no net energy expenditure. If consciousness could survive to the heat-death era, it might experience genuinely timeless existence in a universe where temporal structure has been eliminated through thermodynamic evolution. Such existence would be achieved not by transcending physical law, but by reaching the ultimate end state toward which physical law naturally evolves. However, even this heat-death scenario may not provide genuine timelessness. Quantum mechanics suggests that even in thermal equilibrium, systems continue to undergo quantum fluctuations that create minimal temporal structure. The universe might never reach a completely static state, but would continue to experience rare quantum events that maintain some vestige of temporal flow, even in the far future. The concept of eternal objects from mathematical physics offers another approach to understanding timeless existence. Mathematical structures like numbers, geometric forms, and physical laws appear to exist in a timeless realm that transcends any particular physical implementation. The number 7 is the same whether we count 7 apples today or 7 stars a billion years ago. The Pythagorean theorem describes relationships between geometric forms that remain constant across all times and places. Some philosophers and physicists argue that consciousness might naturally participate in this mathematical realm of eternal objects. If consciousness is fundamentally informational or computational in nature, it might access timeless mathematical structures directly rather than being confined to temporal implementations of these structures in physical systems. This mathematical approach to timeless existence faces the challenge of explaining how timeless mathematical consciousness could interact with or experience the temporal physical world. If consciousness exists in a realm of eternal mathematical objects, it remains unclear how it could have temporal experiences or memories of temporal events. The relationship between timeless mathematical reality and temporal physical reality remains one of the deepest unsolved problems in philosophy of mind and mathematical physics. The anthropic principle adds yet another consideration to evaluating the possibility of timeless existence. The principle observes that the physical constants and laws of our universe appear to be fine-tuned for the existence of complex structures like stars, planets, and life. Small changes in fundamental constants would result in universes where complexity could never arise. This fine-tuning might extend to temporal properties as well. Perhaps consciousness can only arise in universes with specific temporal structures that allow memory formation, information processing, and causal reasoning. If so, then consciousness that achieved truly timeless existence might find itself unable to maintain the temporal capacities that made consciousness possible in the first place. The anthropic perspective suggests that consciousness might be fundamentally temporal, not because of limitations in physical law, but because temporality is necessary for consciousness to exist at all. Escape from time might be logically impossible for conscious beings because consciousness and temporality might be inextricably linked at the deepest conceptual level. As we examine these various approaches to timeless existence within physics, a complex picture emerges. While physics does suggest possible frameworks where timeless existence might be achievable, these frameworks typically require transcending not just ordinary matter and energy, but space-time itself. The practical and theoretical challenges involved are so extreme that timeless existence remains more of a logical possibility than a practical prospect. Furthermore, Even if timeless existence were achievable, it might not constitute escape from time in the sense that conscious beings would find meaningful. Timeless existence might require abandoning the very characteristics of consciousness, such as memory, learning, and temporal experience, that make consciousness valuable to conscious beings in the first place. These considerations prepare us for our final evaluation of whether genuine escape from time is possible, or whether the quest for temporal transcendence might rest on fundamental misunderstandings about the nature of time and existence. The insights from physics suggest that while time is far stranger and more malleable than everyday experience indicates, it might also be far more fundamental to the nature of existence than our quest for escape initially assumed. Our journey through the deepest mysteries of time has taken us from the ancient philosophical puzzles about temporal flow to the cutting-edge theories of quantum gravity and cosmic evolution. We have explored exotic space-time geometries that twist causality into impossible knots, quantum mechanical frameworks that suggest time itself might be emergent from timeless processes, altered states of consciousness that seem to transcend ordinary temporal experience, cosmological scenarios where time becomes local rather than universal, and computational possibilities where reality itself might be digital. Yet as we reach the end of our exploration, a profound realization emerges that transforms our entire understanding of what it means to escape time altogether. The realization is this: every pathway to temporal transcendence we have discovered involves not escaping time, but redefining what time means. Whether through relativistic manipulation, quantum emergence, consciousness alteration, cosmic perspective, or computational simulation, the possibilities for transcendence all require reconceptualizing time's nature, rather than stepping outside temporality entirely. This suggests that the ultimate answer to whether we can escape time altogether might be that escape is impossible, but redefinition is inevitable. Consider what we have learned about time's nature through our exploration. Newtonian absolute time, the rigid universal framework that seemed to trap all existence within inexorable temporal flow, dissolved under Einstein's relativistic analysis. Time revealed itself to be relative, malleable, intimately connected to space, and shaped by motion and gravity. What seemed like an inescapable prison turned out to be a flexible medium that could be stretched, compressed, and curved through physical manipulation. But this relativistic flexibility, remarkable as it is, does not provide escape from time so much as it reveals time's unexpected plasticity. A twin traveling at relativistic speeds experiences time dilation, but remains embedded within space-time throughout the journey. Observers near black holes experience extreme gravitational time effects, but continue to follow world lines through the temporal dimension. Even the exotic, closed time-like curves that permit time travel involve movement through space-time, rather than escape from it. Quantum mechanics initially appeared to offer more radical possibilities. The Wheeler-DeWitt equation's timeless description of the universe, the Page-Wooter's mechanism for emergent temporal experience, and the quantum superposition of temporal states all suggest that time might be constructed from more fundamental, timeless processes. If time emerges from quantum correlations, rather than being fundamental to reality, then perhaps consciousness could access the timeless quantum substrate and achieve genuine temporal transcendence. Yet even these quantum approaches to timelessness involve redefinition rather than escape. The timeless quantum state that underlies temporal experience is not a realm beyond time, but a different way of understanding what time is. If consciousness could access this quantum level directly, it would not escape temporality, but discover that temporality was never what it appeared to be. The transcendence would involve recognizing time's constructed nature rather than leaving time behind. The consciousness studies we explored reveal similar patterns. Meditative traditions that claim to achieve timeless awareness describe states where temporal experience is transformed rather than eliminated. Even the deepest samadhi states or mystical experiences occur within the temporal framework of biological existence, lasting for specific durations and followed by return to ordinary consciousness. The timelessness achieved appears to be a change in how consciousness relates to temporal experience, rather than escape from temporal existence altogether. Psychedelic experiences that seem to transcend normal temporal flow still occur within the biological timeline of the organism, lasting for measurable periods and creating memories that can be recalled in temporal sequence. The apparent temporal transcendence involves altered information processing within the brain, rather than consciousness stepping outside the temporal framework that contains neural activity. The cosmological perspectives we examined offer the most dramatic redefinitions of time's nature. Eternal inflation suggests that our entire cosmic timeline exists as a brief bubble within an eternally inflating multiverse where time becomes local rather than universal. Quantum cosmology proposes that all possible cosmic histories exist simultaneously in timeless superposition. Cyclic universe models replace linear time with circular cosmic rhythms that repeat endlessly. These cosmological scenarios transform our understanding of temporal imprisonment by revealing that what we took to be universal temporal constraints are actually local features of our particular cosmic bubble or quantum branch. The transcendence they offer involves expanding perspective to encompass larger temporal frameworks rather than escaping temporality altogether. Time remains fundamental to cosmic evolution, but becomes far more varied and flexible than we previously imagined. The simulation hypothesis provides perhaps the clearest example of redefinition rather than escape. If our reality is computational, then time becomes the sequence of processing operations rather than a fundamental dimension of existence. This computationally redefined time can be paused, rewound, accelerated, or restructured through programming modifications. Yet even the most exotic temporal manipulations possible within simulated realities involve time as processing sequence rather than elimination of temporality altogether. The quantum gravity theories that probe the deepest foundations of physical reality suggest that space and time themselves might be emergent from more fundamental structures. String theory's pre-temporal dynamics, loop quantum gravity's discrete geometry, and the holographic principle's boundary, encoding all point toward levels of reality that transcend ordinary space-time. Yet even these theories describe the emergence of temporal structure rather than its elimination. They redefine time as emergent rather than fundamental, but temporal relationships remain essential to the emergent reality they describe. This pattern of redefinition rather than escape points toward a deeper insight about the nature of time and existence. Time appears to be so fundamental to the structure of reality, consciousness, and physical law that genuine escape from temporality might be logically incoherent rather than merely practically impossible. The concept of existence beyond time might be like the concept of circular squares or married bachelors, seemingly meaningful but actually self-contradictory when examined closely. Consider what existence beyond time would actually require. Such existence would need to involve no change, no process, no sequence, no development, no experience, no information processing, no memory, no anticipation, no causation, and no interaction. It would be a completely static state that contains no internal structure or activity. But such a state would hardly constitute existence in any meaningful sense for conscious beings, since all the characteristics that make existence valuable to consciousness depend on temporal structure. This suggests that the quest to escape time altogether might be based on a fundamental misunderstanding of what escape would actually entail. The prison metaphor that motivates our quest implies that time constrains us from achieving something better that lies beyond temporal limitations. But if everything valuable about existence depends on temporal structure, then escape from time would not lead to liberation, but to the elimination of everything that makes existence worthwhile. The alternative interpretation that emerges from our exploration is that time is not a prison to be escaped, but a medium to be understood and skillfully navigated. The apparent limitations of temporal existence might arise not from time's fundamental constraints, but from incomplete understanding of time's true nature. As our knowledge of relativity, quantum mechanics, consciousness, cosmology, and computation expands, we discover that time is far more flexible, emergent, and manipulable than everyday experience suggests. This perspective transforms the quest for temporal transcendence from an impossible dream of escape into an achievable goal of deeper understanding. Instead of seeking to leave time behind, we can learn to recognize time's constructed nature and develop greater skill in working with temporal structure. Instead of being imprisoned by time's apparent rigidity, we can discover time's hidden flexibility and learn to navigate temporal experience more effectively. The relativistic realization that time is relative rather than absolute already provides a form of temporal transcendence by revealing that temporal relationships are perspective dependent. The quantum insight that time might be emergent from timeless processes offers transcendence through recognizing time's constructed nature. The consciousness studies that reveal temporal experience's flexibility provide transcendence through developing greater skill in navigating subjective temporality. These forms of transcendence do not require escaping from time, but rather seeing through illusions about time's nature to recognize reality's deeper temporal structure. They suggest that temporal imprisonment arises not from inescapable physical constraints, but from limited understanding of time's true characteristics. As understanding deepens, apparent limitations dissolve, and new possibilities for temporal experience emerge. The cosmological perspectives we explored illustrate this pattern on the largest scales. The discovery that our cosmic timeline exists within a larger multiverse does not provide escape from time, but reveals that temporal structure is far more varied and extensive than we previously realized. The recognition that time might be local rather than universal expands our conception of temporal possibility without eliminating temporality altogether. This expansion of temporal understanding might itself represent the deepest form of transcendence available to conscious beings. Instead of seeking impossible escape from the medium within which all existence unfolds, we can develop increasingly sophisticated appreciation for that medium's remarkable properties. Time reveals itself not as a constraint to be overcome, but as the fundamental creative principle that enables all possibility, all experience, all meaning, and all value. From this perspective, the question of whether we can escape time altogether receives a paradoxical answer. We cannot escape time because escape from time is meaningless for conscious beings, but we can transcend our limited understanding of time to recognize its deeper nature. This transcendence through understanding rather than escape provides all the liberation that conscious existence can coherently achieve. The journey we have taken through the mysteries of time has revealed that temporal transcendence is not about leaving time behind, but about recognizing what time has always been beneath our limited conceptions. Time is not the rigid absolute framework that appears to constrain our everyday experience, but a flexible, emergent, relative phenomenon that enables the very possibility of existence, consciousness, and experience. Perhaps the deepest insight from our exploration is that time and consciousness are so intimately connected that neither can be understood without the other. Consciousness creates temporal experience through its information processing activities, while temporal structure enables consciousness to exist through providing the framework for memory, learning, anticipation, and experience. The relationship is so fundamental that escape from time would necessarily involve escape from consciousness, making temporal transcendence a self-defeating goal for conscious beings. The alternative that emerges is temporal wisdom, the recognition that consciousness and time are partners in the cosmic dance of existence rather than prisoner and captor. This wisdom transforms our relationship to temporal limitations, from struggle against constraints to appreciation for the creative possibilities that temporal structure enables. Instead of seeking escape from time, we can learn to dance more skillfully within time's embrace. Our exploration concludes not with the achievement of temporal escape, but with the recognition that such escape was never necessary. Time reveals itself not as a limitation to be transcended, but as the very medium that makes transcendence possible. The ultimate temporal transcendence is the realization that we have never been imprisoned by time, but have always been free within time's creative embrace, limited only by our understanding of the remarkable possibilities that temporal existence provides. In the end, we discover that the question of whether we can escape time altogether was the wrong question. The right question is whether we can understand time deeply enough to recognize the infinite possibilities for temporal experience that already surround us. The answer to this question is unequivocally yes, and that recognition itself provides all the temporal transcendence that conscious existence can meaningfully achieve.